Good. Well, another second. Two. So welcome, everyone. Thanks for joining the joint whole atmosphere and chemistry climate working group session. So I just a few reminders. The session is being recorded, as you just saw. It's also being streamed on YouTube, just so everyone's aware of that. And the chat will be saved. So we hope that everyone will please follow the guidelines for constructive and thoughtful interactions and throughout the presentations and discussion. And so for this session, we're going to have a series of 4 or 5 10-minute talks, and then a time to answer questions for those previous talks. So we encourage people to type their questions into the chat during the talks, and then we'll have time for some actual answering and discussion of them. And we'll try to take a short break in the middle of the morning and end with some discussion. And then we have some networking time after the end of the session. We'll have some breakout rooms, and which we've labeled with different topics, but we hope everyone will stay around for more informal discussions afterwards. So we will start with Maria Valmartin, and she can start sharing her screen. And the title of her talk is Implementation of Soil Nitrogen Emissions in CESM2 to Study Large-Scale Deployment of Enhanced Rock Weathering with Croplands.
So, Luisa, you need to stop sharing your screen.
Oh, I'm sorry.
I was trying to upload my PPT. There we go. And where is it? There we go. And now it should work. There we go. And I can just remove my screen here. Anyway, so thank you so much for the introduction, Luisa. So I didn't realize that, thank you so much for giving me the 3:30 p.m. talk, which is 8 a.m. there, but I didn't realize that there was a discussion at 9:10, and I have to do a school pickup at 4 p.m. So we'll try to come back in time, but if anything, maybe I can just look at the chat, and if any question, I'm happy to follow up later on, or also keep the conversation via email. So anyway, I'm at the Leverhulme Center for Climate Change Mitigation. This is based at the University of Sheffield. And what I'm going to talk to you today is some of the implementations that we have done at the CLN5 nitrogen cycle, and how we use CSM2 to study the use of enhanced road weathering with croplands to mitigate climate change. So I want to say thank you to some people that have been involved in this work, and also the UK Research Council and Leverhulme Trust for funding. Okay, let's see. Oh, there we go. So just a quick introduction about what is this enhanced road weathering. Well, to meet the 2 degrees temperature target by 2100, we need to drastically reduce greenhouse gas emissions or fossil fuel emissions, but we also need to remove carbon dioxide and greenhouse gases from the atmosphere. So this past year, they had been talking about CDR strategies, carbon dioxide strategies like afforestation, reforestation, BECCS, but enhanced road weathering is one of the strategies that has been proposed and has been recognized also by the United Nations that can help remove carbon dioxide from the atmosphere. So how does enhanced road weathering work? Rain dissolves carbon dioxide from the atmosphere and bring it back to the soil, and there it reacts with the silicate that are for a part of the rocks, like for example basalt has contained silicates, which eventually are going to form cations and bicarbonate that are going to transfer to the ocean And this carbon dioxide is going to be stored there for thousand years. So this is not something new. This reaction had been stabilizing the climate for a million years, but we can accelerate it, for example, applying crushed rocks on croplands, which are acidic. And with this crushed rock, we also increase the surface area for the reaction. So at the Leverhulme Center where I work, we have field trials that are studying the feasibility of basal application in croplands, all the way from the Corn Belt, the energy farm in the US, to sugarcane plantations in Australia. One of the things that these field trials have been finding is that the application of basal treatments reduces N2O emissions, and this is linked to an increase in soil pH. So what I'm showing here on the right, on the left, is how the cumulative N2O fluxes decrease is lower in the basal plot compared to the control plot. And on the right, I have the soil pH, where you can see the opposite, where the soil pH is larger in the basal plot. And this is an example for corn, but in 2017, but we are seeing the same results for miscanthus and also for 4 years that the field trials have been lasting. So this is a simple schematic of the nitrogen cycle. And what I want to highlight here is that anything that changes the soil pH is going to modify the rates in the volatilization, nitrification, and denitrification process. And anything that changes those processes are going to affect emissions of ammonia and nitric oxide and N2O into the atmosphere. And that will have important consequences for atmospheric composition and climate. So what we have done within CSM2 to be able to study the impact of basal applications in atmospheric chemistry and climate is we have implemented a few schemes within the nitrogen cycle in CLM5. So one of the things that we did is we have implemented the soil nitric oxide, and this is based on descent. We have also implemented the soil ammonium volatilization scheme, and this is based on DNDC model, and this work was done by Kamin Fun, and this is actually currently under review in biogeoscience discussion. And we have also modified the nitrification and denitrification in CLF5 to link it to soil pH. So I have highlighted here in this diagram where we have done new implementations and updates, and these changes in the nitrification and denitrification are based on the work of Elena Blanc-Betes and are based on actually on the field trials at the energy farm in the US. As Luisa mentioned last Monday, all these schemes are embedded within the biogeochemical cycle in CLM5. So everything is run by CLM5 with the inputs and fertilizers, soil properties, etc. But any nitrogen losses are going to affect as well the biogeochemical cycle in CLM5. This also one thing that I wanted to highlight is that we have a bidirectional coupling. So that means that we can run this scheme with the nitrogen deposition from from CamChem, but we also can pass the ammonia and nitric oxide and N2O to CamChem if needed. So I have a couple of slides with validation of the model. I have here on the left the annual N2O fluxes with croplands, and we can see that we have a good spatial distribution of these emissions. On the right, I'm showing the seasonality of the N2O emissions in croplands in major crop regions and compared to previous estimates from emissions inventories and previous work. We can see that we have a good seasonal cycle, and we might be overestimating a bit the US and Europe, but in terms of absolute values, we are, CLM5 they capture well the soil N2O emissions over crop regions. And here at the bottom left, I have a comparison of global N2O emissions with previous estimates as well, and we see that we are within a range of previous observations and estimates. So in terms of soil nitric oxide emissions, I think we are on the lower end from previous estimates. I have compared here the global NO emissions with previous estimates, and we have here in red CLM5, and I'm comparing it with HEMCO. And Luisa mentioned HEMCO last Monday, which is an emission inventory that is going to be available for CSM2 if it's not available already. But in terms of the agricultural NO emissions, I think CLM5 is doing a pretty good job. We have in black CLM5 compared to other emissions inventory, and it captures seasonality and pretty much of the crop regions. So there is more work going on with the soil nitric oxide emissions, and this is done by Anthony Wong and Jeff Geddes at University of Boston, and we will hear a little bit more in the next presentation. So how do we model actually the response of CLM5, or well, how do we use CSM2 to look at the effect of basal application in atmospheric composition? So we have here a nitrogen cycle that responds to changes in soil pH. And then we have an enhanced road weathering model developed at Leverhulme Center that projects the changes in soil pH from basal applications. And what I'm showing here on the left is the changes in soil pH that will occur if we apply basal for 10 years on these 5 major crop regions to remove 2 gigatons of carbon dioxide per year. And this work was published last year. So what we had done is I'm going to show some preliminary results where I have run CSM2, so I use CAM4 with Mozart chemistry coupled with CLM5 and at 1 degree resolution, and I have done a 10-year run to look at what are the implications of changing the soil pH on the soil nitrogen emissions and how that impacts atmospheric composition. So here are some results. I'm showing here the changes in soil nitrogen emissions. We have on the top soil N2O, and at the bottom the changes in soil nitric oxide from the treatment, from basal treatment with respect to control. And so blue means decreases, but I have here a summary of the N2O in blue and the NO in red. And you see that actually basal treatment reduces soil N2O and NO in all crop regions where we have applied basal. And then these decreases actually are significant for N2O because they correspond to about 20% of the total N2O emissions globally from cropland. We have also looked at what are the impacts on summertime ground level ozone, and I have focused on the MDA 8 air quality standard, which is the standard for air quality for human health, and also the AOT 40, which is the air quality standard for crop health. And I have here the changes in summertime ozone with the basal treatment with respect to control. I mean, they are not super significant changes, but they can be substantial. For example, the MDA, a change in the 1 or 2 ppb decreases in the MDA 8 air quality standard might offset some of the increases predicted by the increases in ozone projected by the just by climate by 2050, and a small increase in AOT 40, decrease in AOT 40 might increase crop yields in corn and maize and soybean in the US by 2-4%. And this is my last slide. So what we are wanting to just highlight is that we have a flexible framework now to understand the chemistry climate feedbacks resulting from enhanced road weathering applications in croplands. We also have a more complete nitrogen cycle within CLM5 that we can use. Our initial results indicate that basal treatment actually reduces soil N2O and NO emissions, and that might lead to improvement in surface ozone. One of the things that we want to do is to extend the analysis to what are the implications of in soil ammonia, because one of the things that we know is that just from lime applications is that increases in soil pH increase ammonia, so that might have a potential effect on air quality in terms of further production of PM 2.5. So I have here two pictures. One is like to show you how simple it is to apply basal in the field, so it follows like the lime application techniques. And then I have a picture here of many members of the Leverhulme Center when we could meet back in 2019. So we still have, there is a lot of people behind this work and the field trials and lab experiments. And
Great.
this is all what I have to do. Thank you.
Thanks, Maria. So if you have any questions for Maria, please type them in the chat and discuss them later.
Yeah, I might be able to follow up some questions before I have to go, if it's okay. Okay.
Yep. Okay, great. Thanks. Next up is Anthony Wong, who will continue our discussion of soil NO titled, can you share your screen?
Could you hear me?
Yes.
All right, thank you. Yeah.
The title is The Impact of Global Climate and Land Use Change on Soil Reactive Nitrogen Emissions, the Impact on Air Quality.
Hello, everybody. So it's great that Maria's presentation is before me, so that basically this project is totally a spin-off like from the work of Maria and Carmen. So I don't have to do a lot of like extra background introduction on the model. And yeah, so okay, so but why do we care about this problem? It is because soil is actually a very large source of atmospheric reactive nitrogen and therefore secondary air pollutants. Currently, anthropogenic NOx emission is sitting at around 50 teragram nitrogen per year, and soil NOx emissions from natural and from agricultural from soil are around like 20 to 30% of the total anthropogenic NOx emissions. NOx itself is already it has some negative health impact, but arguably more importantly, when it is a vital component for atmospheric photochemical production of ozone, which is another important air pollutant. And currently, non-agricultural ammonia emission is sitting at 7 to 8 teragram nitrogen per year. And you can see that soil ammonia emission is way larger than that number. And once ammonia get emitted into the atmosphere, it will neutralize the acidic negative ions in the atmosphere and form fine particulate matters, which are also very harmful to human beings. And they also have other climate impacts. So, but we have to ask a question about like why are there soil reactive nitrogen emissions in the first place? It turns out it is largely related to soil nitrogen biogeochemistry. So NOx is not the NOx and nitrogen oxides are not the terminal products, but they are the byproducts of NOx of soil nitrification and denitrification. And in addition, ammonia emission is also controlled by the volatilization of ammonium ion because it is highly soluble in water. So because it is biogeochemical in origin, we can already see that there are some factors that would affect soil reactive nitrogen emissions, like temperature, soil moisture, pH, how much nitrogen are there in soil, and decomposition rates and things like that. Apart from these factors, human can also influence soil reactive nitrogen emissions by fertilizer applications and irrigations and other land management practice. So we can start to ask the following questions. We can start to imagine that maybe under a warmer climate, we will have stronger enzymatic activities and stronger ammonia volatilization. Would that mean we will have more soil reactive nitrogen emissions in the future? Would that mean some extra climate penalty on air quality? And also in the future that we have to use more fertilizer to feed more people, would that mean substantially larger soil reactive nitrogen emissions into the atmosphere? So here comes our research questions. How will soil reactive nitrogen emissions look like under climate and land use change, and how would they affect air quality? This is what we are going to study. So this is the basic modeling framework with CLM and ChemCam, which is largely similar to what Maria has introduced. So notably, the code base for the biogeochemistry code base is entirely the same as Maria's code base, but I have implemented the rain pulsing effect of soil NOx. And once we finish using CLM5 BGC to model the soil reactive nitrogen in the future, we will apply them into ChemCam with Mosaic to simulate both like the changes in gas and aerosol trace compositions. So we propose the following CESM experiments. First, we spin up the land model and then do a present day run, and then we will run CLM for each SSP scenario with climate change and climate plus land use change. And then we will pick two largely contrasting scenarios and then apply the 2100 conditions and then run ChemCam with present day soil reactive nitrogen emissions, present day and then the soil reactive nitrogen emissions with climate effects, and soil reactive nitrogen emissions with climate plus land use effects. And here is our present day CLM soil reactive nitrogen emissions. So the number is different from Maria's because I have implemented the rain pulse and I have tuned the nitrification rates over the cropland. So it is higher from Maria's presentation, and now it is NOx is sitting at around 8.3 teragram nitrogen per year, and ammonia is sitting at around 21 teragram nitrogen per year, which is pretty close to other estimates. But for the spatial distribution, we still see quite a lot of like NOx over the high latitudes, and maybe there are too little NOx in somewhere there is like very heavily cropped. And we also see that CLM adds enormous amount of mineral nitrogen to Arctic soil through decomposition, that which may be the cause of high reactive nitrogen emissions over the high latitudes. And we also see some high ammonia emissions over certain deserts, like here, like in Saudi Arabia. So maybe we are overestimating the ammonia emissions over natural ecosystem a bit, and certainly we will have to do more systematic evaluations. And these are the results. These are some very preliminary runs on how climate change may affect climate and land use change may affect soil reactive nitrogen emissions. Bear in mind that our spin-up procedures and the code base is a little bit different. So the result is not directly comparable to the last slide. We use anomaly forcing. We use like the archived CMIP6 output to do an anomaly forcing for the climate run. And then on top of that, we add land use change effects here. We can actually see quite large changes in both like soil NOx and ammonia emissions. And the effect of land use change and climates are very different for different regions. For example, you can see that climate has little effect over the Sahel, but land use change has much larger effects. But over say Eastern US, climate has a large effect on NOx, but the land use is kind of offset that a little bit. So here is because that's all I can share, because like the project is still in a very preliminary stage. But here is the to-do list. Sort of, we want to compare ammonia and NOx emissions with inventories like in more spatial and rigorous manner. And we are working with the CLM people to try to diagnose and solve the spurious NOx emissions in high latitudes. And then like once we get the soil reactive nitrogen emissions, the task may not be as simple as just to replace, just replace the agricultural emission inventories in ChemCam, but we also have to look at the definitions of like what precisely are the agricultural emissions in ChemCam. Does it include like natural emissions, or does it include like other sectors of agriculture? And then perhaps another way to look at whether our soil-reactive nitrogen emissions estimate makes sense is to evaluate our ChemCam simulations with surface concentration and satellite products. And we believe that it will not be the first time that we use similar framework to study the linkage between terrestrial ecosystem and air quality. We believe that there are a lot of potential in this area. Thank you.
Great, thank you, Anthony. That was very nice. And please, listeners, type any questions into the chat and we'll address them in a little bit. And so we'll move on to our next speaker, Aditya Nalam from IISS in Potsdam. Welcome.
Thanks, Louisa. Can you all hear me?
Yes. Welcome.
Awesome. Yes, I also started sharing my screen. Thanks for giving me this opportunity to present my ongoing work on the source attribution of tropospheric ozone in CESM.
We're seeing your presenter mode. Can you switch?
Yes. Does that look?
Perfect.
Yes. Awesome.
Thank you.
So I will be presenting our ongoing work on source attribution of tropospheric ozone in CESM 1.2 Chem 4Chem for the 2000 to 2018 period. And first, I'll start off with the source attribution scheme, which has been published in GMD in 2018. It's called TOS, that is tropospheric ozone attributions of sources with tagging. So I would just refer to this as tagging from now on. I will present to you some important previous results using this particular scheme. And then I will present to you a layout of the planned simulations for this transient period between 2000 and 2018, and some preliminary validation results so far. All right, so a brief schematic of what this tagging really is. As we all know, ozone is formed by photolysis of nitrogen dioxide, and this nitrogen dioxide is formed from the oxidation of nitrogen monoxide or nitrous oxide and oxidized VOCs. So, when we would like to know which source is responsible for a particular molecule of ozone, for example, then we can label the sources based on its emission sector or emission region, and that label is carried on to the output ozone molecule, and in that way the ozone is attributed to its source. So as a simple illustration, we have a NOx tagging simulation where the emitted NO or emitted NOx is labeled with its sources, and a corresponding ozone molecule is labeled with its source. And also, of course, stratospheric influx and lightning NOx are also correspondingly labeled with labeled to the particular ozone molecule in the simulation. Similarly, for the VOC tagging, the VOC molecules are labeled to their sources, and their corresponding ozone, the corresponding resulting ozone, is labeled with the tag or the label on the emitted VOC molecule. And it's not just ozone, but also all of its intermediate species that are participating in the reaction sequence carry the same tag. So for a further illustration of this, I would refer to for more information, again, I would refer to this 2018 paper by GMD, and you can get much more detailed information about it. again, as a example of its application, my group has also published another paper in ACP in 2020, where we used 2010 HTAP emissions. Two model runs were performed, that is NOx tag and VOC tag run. And so here, okay, and we also used the 2010 specified dynamics configuration. And what I would like to illustrate here is how this tagged, resulting tagged ozone looks like. So here you can see in the NOx tagging simulation, there's this total ozone, and there are these tagged components of ozone. So ozone attributed to lightning is shown in this second panel, and ozone attributed to emissions from oceanic NOx sources like shipping are shown here. So the ozone resulting from it is predominantly over ocean regions, but it's also spread out across into the land regions, which is pretty clearly illustrated over here. Similarly, anthropogenic emissions from North America, anthropogenic emissions from Europe, and anthropogenic NOx emissions from East Asia are also tagged, and the resulting tagged ozone is mapped here. Now, what I'm showing you here are the what I call source regions. What you can see in the previous slide is that the anthropogenic emissions are labeled based on their source region identity, and these regions are defined in the HTAP ensemble. And these regions have been tagged in our tagging system, and we can have resulting outputs like this, for instance. Similarly, for VOC tagging, we have the total surface ozone, which is of course the same as the total surface ozone and the NOx tag simulation. And most of the ozone from this is can be attributed to background methane and biogenic emissions, whereas the anthropogenic tags contribute very less, because the contribution of anthropogenic VOC emissions is much smaller in the global scale. So that's why you can see such a pattern. So this is just a brief illustration of how this tagging system works and how it can be applied. Now I will move on to my ongoing work on simulating this tropospheric ozone with tagging for the historical period of between 2000 to 2018. Previously, it was only done for the year 2010, and now we're going to be extending it to this historical transient simulation. A brief schematic of all of the settings that are used in this study. So firstly, we'll be using a 2-degree resolution model, 56 vertical levels, which is the standard configuration. And it's simulated for the year 2000 to 2010. Separate simulations are performed for NOx and VOC. This is all done also in the previous papers. The transient emissions, that is emissions from the year 2000 to 2018, are derived from CAMS inventory, that is Copernicus Air Monitoring Service inventory. And the number of tags that are being implemented in this study include the regional tags, that is the source regions that we've seen in the previous slide, and also tagging the emission control areas for shipping, which I will elaborate more in the next slide. Then the stratospheric boundary conditions are also relaxed to the annual values. Here, as you can see here, and these annual values have been taken from one of the CMIP 6 ensemble members, that is CESM2 vacuum. And we've used the MERA2 reanalysis data for the 2000 to 2018 period, because it had the consistent version of reanalysis dataset. Another setting that we had to use is the relaxation of nudging and make it more towards a free running case. This was based on a suggestion from Louisa when we were having problems with this, and I will elaborate more in the next slide. So what this essentially does. Sorry?
2 minutes, please finish up. 2 minutes.
Oh, okay. So what we've done here is that we compared the simulated and observed ozone with relaxation and without relaxation, and we've seen that this purple line, that is met relax of 0.2, is within the HTAP ensemble range, and it's also closer to this black line, which is the observations. I will skip the next slide because it's I'm running out of time. So what we've implemented in the NOx tagging is we've tagged a lot of land-based regions and also oceanic regions. And here we've implemented the tagging for emission control areas. As you can see, these pink regions here, which are the regions really close to the coastline. And this can give us further insight about how the near coast emissions are differently affecting the air quality when compared to the open ocean NOx emissions. Whereas that's not the case for VOCs, because not much VOC emissions is happening directly in the open ocean. So yes, this is essentially it. So this modified chemical mechanism has been implemented, and I've also illustrated some of these aspects, and then I've also illustrated how the I've also summarized our settings for the ongoing simulations, and also explained the inclusion of emission control area tags. So yes, this is the end of it, and thanks a lot for this opportunity, and questions and comments and suggestions are welcome. Thanks a lot.
Great, thank you. Nice to see all this work continuing. And Wenfu's up next, improving fire representation in Musica version 0. Thanks, Wenfu. Go ahead.
Can you see my screen and hear me okay? I'll just start. Hello, everyone. Today, I will share some preliminary results from our recent work on improving fire representation in the Musica version 0 model. We know plume rise and diurnal cycle of fires are two important features. They are both important because they impact the fire emission transport, lifetime chemistry, and also their impacts. So this figure on the left shows the physical processes involved in fire plume rise. And this figure on the right shows the averaged fire diurnal cycle over the US. And the fire relative power and fire emissions peak at early afternoon, generally during daytime. And this would have important implication for secondary pollutants formation and also the atmospheric chemistry. And there are different ways to apply diurnal cycle to fire emissions. For example, we could apply a single diurnal cycle to all fires, and we could also calculate fire diurnal cycle using satellite FRP data. And in this way, every fire would have its own diurnal cycle. But in this presentation, we will only focus on this one simple approach, which is applying the same characteristic diurnal cycle to all fires. And there are also different ways to apply plume injection to fire emissions. For example, we can use climatology plume injection profiles as shown on this slide. to our fires, and we could also calculate plume rise within the model online for individual fires. And as the first step of this work, in this presentation, we will only focus on applying this climatology plume rise, plume injection profile to our fires. And I just realized my presentation is the first one in this session that involves Musica, although there will be great ones afterwards. So here is a very brief introduction to the model. So Musica version 0 is a regionally refined version of CAM-CAM, and this grid is with the refinement over the corners region, and the resolution outside is about 1 degree, and the resolution within is about 14 kilometer. At this high resolution, we hope the features of fire, such as diurnal cycle and plume rise, could play a more important role. And this video here just shows the CO concentration at surface modeled by Musica, demonstrating the high resolution capability. We focus on 4 Musica simulations for this presentation. The control run, which does not have any diurnal cycle or plume rise, and a sensitivity run with only diurnal cycle, and a sensitivity run with only plume rise, and lastly, a sensitivity run with both plume rise and diurnal cycle. And to evaluate the model results, we use observations during the 5XAQ field campaign that was conducted in 2019 summer. So 5XAQ provide comprehensive observations to investigate the impact on air quality and climate from the wildfires and also agricultural fires across the continental US. And as shown by this figure on the right, the first part of the campaign was based in Boise, Idaho, focusing on wildfires. And the second part of the campaign was based in Salina, Kansas, focusing on the agricultural fires there. And this table shows the comparisons of Musica simulations with the airborne measurements of CO and NOx made by the DC-8 aircraft. And overall, adding diurnal cycle and all plume rise can improve the model agreement with the airborne observations during the campaign, especially for NOx. And this bar plot is more intuitive, showing the reduced NOx bias. We also looked at the Williams Flats fire as a case study. This Williams Flats fire was the largest fire sampled during the 5XAQ. So if you look at this lower panel, the model grids within the plume are shown along with the CO concentrations and wind field at the model surface layer. And the location of the 1-minute merged observations from the DC-8 aircraft are also shown by these black lines and the black dots. So as we can see, the resolution of Musica version 0, which is around 14 kilometer over corners, has come down to the scale that is approximately comparable to the fire plume from this fire, and also the 1-minute merged airborne observations. This slide shows the modeled vertical profile plots of the wind CO concentrations and the PBL height that are averaged over this whole region shown here. So as we can see, the CO profiles in these four simulations are different due to the diurnal cycle or plume rise. And we know diurnal cycle and plume rise can change the transport of the fire emitted trace gases and aerosols, because when they are emitted at different time of a day and a different altitude, they are subject to different meteorological conditions. and would be transported differently. And besides meteorology, we also looked at the impact of plume rise and the diurnal cycle of fire emissions on the atmospheric chemistry. This slide shows the time series of a few modeled chemical species. So the modeled concentrations of these species are averaged over the whole region and also averaged from the surface to the 500 millibar. And the black line represents the control run, and the colored lines represent the sensitivity runs. And the dashed line shows the results from a simulation, musical simulation with fire turned off, just added here as a reference. So as we can see, the simulation with only plume rise, which is the red line, is closer to the control run comparing to the other two runs with diurnal cycle. So this seems to indicate that at least for this case, fire diurnal cycle has a stronger impact on the chemistry than the plume rise. And also, as we know, atmospheric background oxidation capacity, for example, the OH diurnal profile, as shown on the bottom lower right panel, has a strong diurnal cycle, strong diurnal variations. So even if the daily total fire emissions are the same for all these simulations, the simulations with diurnal cycle has stronger emissions of primary species during the daytime, and that corresponds to the peak sunlight and the photolysis strength. And this is my last slide, and showing the implications and the next steps. One thing I would like to say is that plume rise and the diurnal cycle should be both considered together simultaneously, because plume rise is strongly influenced by fire diurnal cycle. And in addition, diurnal cycle and plume rise can both interact with meteorological conditions. And also, I would like to say, if you are interested in this work, please talk to me or send me an email. And thank you.
Great, thank you, Wenfu. As usual, I've done a poor job in keeping everyone on time. Wenfu, that was fine. But so we can spend a couple minutes on questions. I think most of them have been answered in the chat, but I wondered if Stephanie and Anthony had anything more they wanted to mention about the NOx emissions in the Arctic, because that certainly was a striking feature of those simulations. And if anyone else has a question they haven't answered, you can ask, you can raise your hand. Go ahead, Anthony. Do you have anything more you wanted to?
It is largely answered there, but I just want to emphasize the second point that I think a lot of biogeochemists have a lot of biogeochemists have said that a warmer climate in the future will activate the biogeochemical cycle in the Arctic. So that's why it is even more important for us to get a reasonable value of present day NOx emission over the Arctic, so that we can model that effect more accurately. Yes.
Yeah. Wenfu, do you want to say anything about Simone's question about the CO, smaller CO?
Yeah, so when I apply diurnal cycle to fire emissions, I make sure the emissions for a UTC day is conserved, but it's not conserved for a local day. So it's possible after applying the diurnal cycle, the emissions actually from the second UTC day was moved from a second local day was moved to this to this day. Because this Williams Flats fire is not a one-day fire, it continued for many days.
Yeah.
Seems complicated to understand for sure how that would work, but yeah, thanks.
Okay, if there are no more questions at the moment, please feel free to ask anything more in the chat. And maybe we should move on to the next set of talks.
Louisa, should I just chair these? I think
That would be great. Thanks.
Okay,
Nick.
great. And then I'm just clarifying, the Dusong's talk has 15 minutes. Looking at the schedule, and there's like it's 15 and then 10, 10, 10. Oh, sorry, you're muted.
I prepared 10-minute talk anyway, so I think
Okay.
we can
Yeah,
just
so,
have 5 minutes discussion.
I think that was supposed to be 15 minutes was supposed to be for questions and discussion. So we could
Okay.
spend another 5 minutes on questions. Does anyone else have any more questions? Because when I first made the schedule, I had 5 talks, and there were, and I didn't properly adjust the times. So people are, Aditya, there's a question for you. Would you like to answer that? Can you elaborate more on the overestimation of surface ozone that your model has addressed? For example, what is the detailed pathways to mitigate the overestimates of surface ozone physical or chemical processes?
Thanks, Lucy, for pointing that out, because I was already halfway through my typing.
Oh.
Yes. All right. Talking about it makes it much easier. Yes, this overestimation feature using this MERA2 reanalysis has been a feature also observed in CESM2, according to one of Louisa's emails. And thanks to Louisa, because she really helped us out in having this idea about relaxing this nudge between prescribed meteorology and the meteorology that is being used. And when the nudging is relaxed more towards the free-running case, then the simulated surface ozone also reduces, and this overestimation also reduces. But to elaborate more on the physical and chemical processes that are responsible for this, again, I'm not really sure how this works in the model. Yeah, this has been a prominent feature that has been observed even in both in the older version that I use, that is CESM 1.2, and also in the more recent CESM 2 simulations. Yes.
Yeah, it's definitely an ongoing issue, and a number of us have been investigating the impacts of nudging, and there are a lot of options for how to actually set that up. So that's another aspect of this model simulations that everybody can explore and try to help understand the sensitivities of it. Well, so maybe in the interest of trying to keep on time, we could just go on to the next sessions.
Sounds good. Our first speaker in the next session is Dusong Zhou from NCAR. He's going to talk about effective grid resolution on urban air quality with Musica version 0.
Okay, can you see my screen?
Yep.
Okay, thank you. So yeah, good morning, everyone. So today I'm going to talk about effects of grid resolution on urban air quality simulation with Musica version 0. So I would like to start the talk with this schematic diagram. So these represent model grid size and values inside the mean nitrogen oxide in each grid cell simulated by model. In this fine grid model, you can simulate this urban center and down into a rural area like this. But when we use coarse model, then there is an artificial mixing due to the coarse grid. So in terms of aerosol formation, of course, for gas formation, but here I present a schematic diagram for aerosol formation. So with less annual concentration in urban centers in coarse grid model can lead to different formation and loss rate. So the goal of this research is to investigate the effect of this grid resolution on gas and aerosol concentrations and chemistry, especially over urban regions. As you already know from presentations on Monday and yesterday and Wenfu's presentation just before this talk, musical version 0, which was released in the latest CSM version 2.2, has some capability to use spectral elements with regional refinement grid, like this over Konos or this over the Arctic region. These grids are provided by default in CSM 2.2, but you can also make your own grid for your region of interest. And my region of interest is South Korea, especially during Kuroseki campaign in 2016. South Korea has very small urban area with high air pollution, as shown on the right figure by NASA showing night lights. So it is good reason to investigate the effects of grid resolution on chemistry. So these are my grids I designed for the Kuroseki campaign. I made two global grids, NE30 and NE60. And NE30 correspond to 1 degree or 100 kilometer resolution. And NE60 correspond to 0.5 degree or 50 kilometer resolution. And there are two regional refinement grids correspond to 14 kilometer and 7 kilometer over South Korea. And this slide shows the same grids for Asia only. And here for South Korea. So you can see this very fine scale structure here in NE30 by 16 grid. Let me show you some preliminary results I have from this musical version 0 simulation. So here, model dynamics, physics, chemistry, and emissions are the same for all grids, but the grid resolution is the only thing that they are different. So as you can see from these figures for black carbon concentrations, simulation results are quite different. Global grids failed to resolve high concentrations over urban areas in China. And the plot is still showing black carbon concentration, but over Korea. And the black carbon here is chemically inert in the model, so generally follows the emission pattern. And global coarse grids failed to resolve high concentrations over Seoul metropolitan area. But these two regional refinement grids shows some high pollution over Seoul area, and especially this NE30 by 16 model captures fine structure of cities in Korea. And this plot is for ozone concentration. And again, the fine grid model simulates some fine scale features like some NOx titration. So ozone concentration is very low, but the coarse model failed to simulate NOx titration effect and simulate high ozone concentration over urban area. And this slide shows the model evaluation against aircraft measurements during Kuroseki campaign. So here, different colors indicate simulation results from different model grid simulations. So boxes are observations here with median and mean and percentile values. So you can just see the spread modeled values here, especially for carbon monoxide. Concentrations are very similar at the surface, but they are different in the upper troposphere, like a factor of 2 differences between the model grid settings. And generally, fine grid resolution shows higher CO mixing ratio. And for sulfur dioxide, they are different at the surface, but very similar in the upper troposphere. So the effect of grid resolution on different chemical species are different. And here I show you the same evaluation plot against force AQ aircraft measurement, but for aerosols. So for organic aerosol, black carbon, nitrate, and sulfate. So you can find that grid resolution is important for some species, but not for all. So for example, here organic aerosol concentrations are similar across different grid resolutions. And I think for organic aerosol formation, because we need more oxidation time in the real atmosphere than other aerosols like black carbon. So artificial mixing due to pulse grid model resolution is not important for organic aerosol formation in this case. Another thing you can notice from these figures is that the model underestimates organic aerosol and nitrate and shows a relatively good agreement with observed black carbon and sulfate. Actually, I think this is a widely known problem for chemistry models. So usually chemistry models simulate black carbon and sulfate very well, but underestimate organic aerosol concentrations, and models overestimate or underestimate nitrate aerosols. So in the next step, we are going to investigate the reason for the underestimation of organic aerosols and nitrate during the Course AQ campaign. So in addition to spatial resolution I showed you earlier, another thing we are developing right now in Musica is to investigate the effects of temporal resolution on chemistry by applying Diurnal cycle for emissions. So Wenfu showed Diurnal cycle is important for fire emissions earlier, but it can be also important for anthropogenic emissions as well. And currently, we don't have the Diurnal cycle emissions in Musica, but it can be important for some species. So with some Diurnal cycle factors shown on this upper left side with time zone, we can apply some global hourly Diurnal cycle factors to monthly average emissions. And we looked at the differences in ozone concentration shown on the right side. And we found that, okay, thanks. We found that average ozone was increased over the US, Europe, and Asia continental regions in terms of mean ozone concentration. And this result is for May, June 2016 average ozone here. And the average ozone increase in the previous slide is due to actually nighttime ozone increase in the model. So here I show you mean Diurnal variation of NOx, ozone, CO, and OH at the surface layer in Seoul. And black line shows the base case without Diurnal cycle, and red line shows the model with Diurnal cycle of NOx emissions. And because of reduced NOx emissions during the nighttime, we have less ozone loss reactions. So we have higher ozone concentration. And during the daytime, the model with Diurnal cycle of NOx emissions showed slightly less ozone concentrations and OH and some changes in CO concentration. And this result is the just test case with NOx Diurnal cycle with only some universal factors for all sectors. But we are going to implement some sector-specific Diurnal profile factors. So you can see here that different emission sectors have different Diurnal cycle factors. So for example, here you can see more bluish and reddish colors in residential sector factors, but energy industry sector shows some values close to 1. So we are going to implement these, and these factors can also be used in HEMCO emission processing tool in the future as well. So here is the summary of this talk and ongoing work plan. So we constructed new model grids using Musica version 0 and could investigate the effects of horizontal resolution on simulations, especially over Korea, where there are small urban areas with high population. And I'm happy to take any questions, of course, in the chat. Thank you.
All right. Thanks very much, Jisong. There's some questions in the chat, and if they don't get answered, we can talk about them in the question and discussion session. So our next speaker is Forrest Lacey from NCAR, who's going to talk about chem model assumptions and their impact on health-relevant pollutants and outcomes.
Sorry, just okay. Back to the beginning. Okay, can you guys see everything okay? Okay, great. Thanks, Dusong, for the really nice talk. I'm going to talk to you now about some experiments that myself and Becky Schwantes, along with all the other co-authors, have been running, again, using Musica version 0 to estimate how model assumptions impact both concentrations of health-relevant pollutants and their health outcomes. And as kind of an introduction to this, I know that Musica has been introduced quite a bit, but why specifically focus on health-relevant pollutants within a global model is pretty relevant from the effects that we've seen in the last year. Things like really large-scale wildfires that have a lot of transport, to COVID-19, to extreme weather events being a transport mechanism as well. So Musica version 0, again, was released with CESM 2.2. And at finer resolution, the specific case that we're using is a 1 degree global grid with 1/8 degree refinement over CONUS. And the assumption is that we're going to better resolve emissions, and chemistry will be more accurately represented. And we'll also be able to calculate pollutants at human exposure relevant scales, which is around the 10 kilometers or so. So the framework for these experiments is that we wanted to test two things particular with this setup. So we wanted to test the impact of horizontal scale. So we ran with both a 1 degree global grid, or the NE30, and then also with the aforementioned 1 degree with 1/8 degree magnification over CONUS, which is the NE0 by 30 by 8 CONUS grid. Additionally, we wanted to test chemical complexity and see how that impacted health-relevant pollutants and their concentrations. So we ran with the Mozart TS1 mechanism, which is the base chemical mechanism. And additionally, we ran with the Mozart TS 2.1 mechanism, which improved isoprene and terpene chemistry, in addition to adding both a high and low NOx pathway for SOA formation. And we'll see why that's important when I get to the results. So the science question that we're aiming to answer here is, how do these changes in model assumptions impact both estimates of ambient air quality and the resulting health impacts? Because these two are tied, but not necessarily at the same level. And I will mention that some of this work was presented yesterday. So go back to my talk yesterday for a little bit more complete model evaluation or model description. But I did want to show two things here. One is that we did evaluate the model both with respect to flight campaigns and with respect to surface observations. And for the work presented here, we did make one change specifically on how we're evaluating the model, or how we're using the model output for health relevant metrics. But this is Becky's work looking at the 5 field campaigns over the US. And as you can see, the best performing model is the regional refined TS 2.1 case in most pollutants. So right here, we're showing NO, but she's done this analysis for most ozone precursors. And this is the update that I wanted to talk about with the results that we had from this. So what's being shown here is the model first level ozone. And this is a correlation plot with all EPA AQS sites. And the one on the left is showing model first level. And the second one is showing a surface corrected ozone which takes in the surface roughness and deposition velocity as a correction factor to reduce the ozone concentrations at the surface versus the first level. And this is kind of a spatial map showing, this is for June, July, August, average concentrations. And here you can really see that we're reducing, with the surface correction, we're reducing the surface ozone that we're calculating within the model. And this is kind of showing it on a regional basis. So here I've picked out 2 of the EPA regions and looked at kind of the daily MDA8 concentrations, both with the correction and without the correction. And here you can see we're falling much closer to the observed MDA8, which is the blue line on the bottom. And the green is the surface corrected, and then the top Musica line is the first level ozone. So this surface correction has really brought us closer to the observations, which I think is important when evaluating this as a health relevant metric. And for reference, the red line shown here, that's what's called the counterfactual, and I'll get into that in the next slide. But below that level is the point that we can say that we do not have a statistical impact of ozone concentrations on human health. So that level is at 26.7 for some of the calculations. It varies depending on what metric you use. But I just wanted that on there as a reference to show that particularly in EPA Region 8, which is the Mountain West where we are consistently above the health relevant metric for MDA8 ozone. So the methods of how we are doing these health impact calculations is using what's called a beta function. And this is the general form is shown here, where you have some change in mortality is a function of some incidence rate minus a beta function, or the inverse of the beta function, where these are basically calculated as the hazard ratio, or the kind of percent increase or increased likelihood that you will have of a specific disease outcome based on studies that have looked at hospitalizations and death counts, and then created this statistical relationship. For this case, we're evaluating both ambient PM2.5 and ozone. And for PM2.5, we're using the Global Exposure Mortality Model, or GEM, which is adapted from Burnett et al. 2018. And this is the most up-to-date cohort study. It includes a number of cohorts, not just in the US and Europe, but also in China. And for ozone, we're using beta functions from the ACS CPS2 study. And I'll go over this quickly, but the baseline mortality rates that we're getting are from BenMap, which is a EPA model used for health impact analysis. And I've also looked at them from the CDC Wonder and compared how the different formulations of those work. And then just the final 3 slides here, I'll try and go through quickly for the sake of time. But this is kind of the nuts and bolts of the findings that we have here. And probably to me, and I think to the other authors on the paper, one of the most novel findings of this work is that both resolution and chemical complexity are of similar importance when you're looking at how they impact human health. So what we have here in these plots is the attributable deaths for each region. Green is for the regional refined, blue is for the 1 degree model, and the hatched is for the more complex chemistry case.
2 minutes.
So here we have basically, if you look at this difference plot, I think this is really highlighting what I'm trying to show. Basically, this is now showing the shifts between those, and green and blue are kind of equal magnitude here, especially when you're in populated regions such as EPA Region 2, which is New York, New Jersey, and EPA Region 9, which is includes California. So that's where we're seeing the largest impacts of both resolution and chemistry. Ozone, I did want to put this in here for the sake of being complete. We're updating this analysis based on some discussions I've had with the health community in general. And but the one takeaway here is that resolution seems to be more important when it comes to ozone impacts, not as much chemistry. And you can kind of see that if you're looking at concentrations. The largest concentration changes are due to ozone and not as much with chemistry. And then finally, these are kind of the total number of attributable deaths for each of the different runs. And here you can see for PM 2.5, we're really getting similar values, around 20,000 for a change either in resolution or in chemistry. So that's really highlights how similar they are. And in ozone, you're seeing that most of the results are from the change in resolution. We are updating this, and our next set of simulations will include a number of changes, including ones mentioned in previous talks. And we're also working with epidemiologists to include errors due to assumptions of health relevant functions and data. And with that, I'll end.
All right, thanks, Forrest. If anyone has questions for Forrest right now, you can type them in the chat, or we can revisit them at the question discussion break. So our next speaker is Tibor Fritz from MIT, who's going to talk about CESM2 GC, Geochem as a chemistry option in CESM.
All right, thank you. Can you see my screen?
Yep.
All right, thank you. So in this presentation, I wanted to give a brief overview of CESM2 GC, which embeds the geochem chemistry mechanism as a new chemistry option within CESM2. So in this presentation, I'm going to focus on a model intercomparison between CESM2 GC, ChemChem, and the geochem CTM. So CESM2 has historically been relying on the Mozart family of chemical mechanisms to perform atmospheric chemistry. So here we propose to add a new chemistry option using the geochem chemistry mechanism that stands alongside Mozart. So this coupling that we named CESM2 GC relies on the out-of-the-box geochem source code and requires no further modifications. And this new coupling allows for a fair ChemChem to geochem intercomparison, both embedded within CESM2, and also acts as a two-way channel for improvements in both communities. So in terms of the technical description, CESM2 GC features a coupling with MAM4, where aerosols that overlap between the geochem chemistry mechanism and MAM, such as black carbon and primary organic matter, are essentially passed from MAM to geochem. Geochem performs its chemistry, and then the tendencies are then passed back onto MAM. For other aerosols that do not overlap between the two models, they're just handed off to geochem. And here I want to point out that we use the geochem with the complex SOA option to facilitate the mapping between the SOA species in geochem and the VBS scheme in MAM. For dry deposition, we have two options that are currently implemented in CESM2 GC. The first one is the same as what Mozart is doing, where it uses the dry deposition velocities computed by CLM and pass through the coupler to CAM. The other option is to directly pass the length tabs and the leaf area indices from CLM to CAM, and then to use the geochem dry deposition routines to compute the dry deposition velocities. For wet deposition, we rely on the new scheme to compute the washout of gaseous species and geochem aerosols. For photolysis, we rely on FastGX, which is the module that computes photolysis rates within geochem. And emissions are handled through HEMCO, which lives at a higher level than the chemistry, and this allows for essentially identical emissions between ChemChem and geochem. So in this presentation, we provide a three-way model intercomparison between CESM2 GC, ChemChem, and the geochem CTM. And here I want to make sure that essentially as many things as possible are identical between the three simulations. So first of all, whenever possible, choose emissions through HEMCO in all three models, unless we have a better option in any simulation. So for instance, in CESM2, there's an online option to compute lightning NOx, which there's not in the geochem CTM. So that in that case, in the first two simulations, we're only using online lightning NOx emissions or biogenic emissions, for instance. And all three simulations also use specified dynamics using NAPA2. The resolution is approximately identical in all three simulations, and whenever possible, we also use online land types. CAMCAM is running with the TS1 chemistry mechanism with simple VBS, whereas the two geoschem simulation use the complex SOA option and use fast GX with catalysis. And in terms of the validation experiments that I'm going to show in the next few slides, I compare individual processes. So I validate individual processes such as dry and wet deposition fluxes of ozone, nitrogen, and sulfur that I compare against the literature, and also compare full model results by looking at surface composition of ozone against ground station measurements over the US and over Europe. Also compare vertical profiles of ozone and other species against ozone song climatology and aircraft company measurements. And finally, I also look at column totals of ozone by comparing to the observations of RMI and MLS, and also a CO column with the dataset from MOPIT. So now let's move on to the intercomparison. So I start by comparing the wet deposition tendencies of nitrogen through the three models. So from top to bottom, CSM2GC, CAMCAM, and the geoschem CTM. And I compare those results to observations for the year 2005 from Vettel. And all models provide consistent results with a correction coefficient of 0.66. But we note that there's a slight negative bias at like higher wet deposition fluxes, let's say at values greater than 5, where all three models have kind of a negative bias. But we know that the slope from the regression line is closer to the parity line in the case of CSM2GC. For the sulfur wet deposition, we do the same comparison where we compare all three models to the same rainwater composition measurements for the year 2005. So what we first see is that all three models kind of predict the same trend, but that this trend is far away from the parity line. And so the model results were obtained for the year 2016, whereas the measurements were done for 2005. And I think this discrepancy is explained by the fact that there's been a decrease that's been observed in the literature in the deposition of sulfur at a rate of approximately -1 kilogram sulfur per hectare per year since the early 2000s up until now. And that's been observed in a number of studies that have been recently published. When I look at column totals, here we compare the observations from OMI MLS for total ozone column to the biases that we observe in CSM2GC and CAMCAM. So I find that there's an annual bias in column ozone of approximately -8 Dobson units for CSM2GC, whereas the same simulation in CAMCAM yields a bias of +6.5 Dobson units when you average annually. But I find there's also strong seasonal variations in the total column ozone, where, for instance, for CSMGC, it varies between -16 to -6 Dobson units, whereas in CAMCAM, it's bounded between -3 and +7 Dobson units. And when you look at the tropospheric and stratospheric ozone column independently, I find that CSMGC underestimates both of those by approximately -2 and -6 Dobson units respectively, whereas CAMCAM has a larger bias in magnitude for the tropospheric ozone column, but does slightly better in the stratosphere. Now I compare the vertical profiles of ozone by comparing the results from the CSM2GC and CAMCAM simulations to ozone songs. So if you look, for instance, at the first column in the tropics, you see that both CAMCAM and geoschem, the results from both CAMCAM and geoschem are relatively close, and they estimate roughly similar ozone mixing ratios. In the middle column, in the mid-latitudes, in the troposphere, you see that geoschem is kind of lying underneath the ozone climatology and underneath the results of CAMCAM as well. But it does a bit, it lies closer to the ozone song climatology when you look at pressures of 250 hectopascals and 50 hectopascals in the stratosphere. But higher latitudes, so closer to the poles, geoschem underpredicts the ozone mixing ratios throughout the troposphere. I can also compare the same results to aircraft campaigns to kind of have an idea of the vertical profiles of different species other than ozone. And we see once again that CSMGC in red underestimates the ozone mixing ratios at different latitude and seasons, whereas CAMCAM is closer to the observations. But for other species, we see that both models are relatively consistent and quite close to the observations. And finally,
minutes.
when I look at the MOPIT's carbon monoxide comparison, I see that, for instance, in CSMGC, there's a small annually average column ozone bias, carbon monoxide bias. But both models still underestimate carbon monoxide in the northern hemisphere, but this magnitude is smaller in CSM2GC. And finally, looking at surface ozone, here we compare the results of CSM2GC, CAMCHEM, and the GeoSCAM CTM to ground station measurements from the EPA and the European Environmental Agency. And I find that generally CSM2GC has a lower estimate of surface ozone mixing ratio compared to the other two models, but generally agrees quite well with the observations. So for instance, if you look at the correlation coefficient in North America, CSM2GC predicts a correlation coefficient of like almost 0.5. The GeoSCAM CTM does a bit better, but over Europe, CSM2GC performs better. So to wrap up this presentation, we included the GeoSCAM chemistry mechanism within CSM2, and we provide a fair comparison with identical emissions and identical meteorology between CAMCHEM and GeoSCAM, both embedded within CSM2. I find that CSM2GC predicts a lower tropospheric ozone mixing ratio than CAMCHEM towards the surface, and also allows for reduced column carbon monoxide bias compared to CAMCHEM. And finally, ozone and NO2 surface mixing ratios from CSM2GC agree reasonably with ground measurements. So if you have any questions regarding the methodology or the results, just let me know during the discussion session or just type it in the chat. Thank you.
Thanks, Thibaut. Yeah, there's a few questions in the chat right now. And if anyone else has any questions, feel free to type them in. Our next speaker is Ben Gobert from NCAR, who's going to talk about aerosol data assimilation in CESM.
Good morning, people in the US. Can you see my screen?
Yep.
Full screen now. Yes. All right. I'm going to show some very preliminary work on assimilating AOD to constrain aerosol concentrations and emissions. So basically, when we do a regular simulation.
Ben, we're not seeing your presentation mode.
Oh, wait, sharing is proven. I guess I'll share my desktop.
Yeah, that's good. Yep, that's good.
So basically, get a fire, then MODIS is able to detect fire counts or burnt area. And those are translated into emissions. For instance, Finn is using the burn area from MODIS and VIIRS, and provide emissions of, according to emission, you get the burn area and you convert that into fluxes for the different chemicals. So here for CO, and you can see very strong correlation between CO, BC, and POM, but also other VOCs. So the basic idea is then when you run CAMCHEM, you get aerosol mass concentrations that translate into AOD. And then you compare, you interpolate the AOD to the MODIS location and compare MODIS observations with simulation and correct the concentrations, but also emissions related to POM and BC. And so if I show here the CO is because I'm using the CO tags to differentiate between anthropogenic and biomass burning. So then I can update the files and having updating emissions in my next forecast in addition to the initial conditions updates. So I'm running the CSM 2.2 with nudging to the DART CAM reanalysis. for my spin-up. And then I'm using the regular CSM 2.2 options with TS1 chemistry and MEM4 and VBS. One of the updates is the FIN 2.2 emissions. They include VIRs, so they're a bit higher than the 1.5. And the new CAMPS emissions have been released a couple of months ago. That is actually EDGAR for the 2015, which is what I'm looking at. So what I did is I'm applying perturbation to the nudging parameters to have an ensemble of different physical and chemical environment. So nudging parameters are the strengths of the nudging to U, V, and T. So it would be 15 hours on average, more or less 0.15, so a couple of 9 hours to 25 hours nudging. So that allows to first perturbation in the physical parameters. But then later on, I'm starting the assimilation of those weather parameters, so then I don't need to nudge anymore. But I'm applying perturbation for the dust and sea salt, biomass burning, and anthropogenic that are completely different. So I'm perturbing the global dust factor, global sea salt factor to have perturbation in the respective aerosols. And all of the gases and aerosol direct emissions from FIN and CAMPS, which would be independent from the biogenic as well. So that hopefully the ensemble covariances between all of those parameters would be correlated when it's needed, where the transport errors are important for all of them, but then independent when the sources are different, to be able to differentiate the different aerosol types. Because the problem is that you have one column observations that is used to update 27 state variables actually, and I'm adding 2 emission fluxes to that. So it's largely under constraint. So you want to be able to have an ensemble that guides you the differences between sulfate, dust, sea salt, and the different sources of black carbon and primary organic and secondary organic as well. So, and the respective numbers. When I'm doing the weather assimilation, I'm just changing the UV, specific humidity and surface pressure according to the meteorological observations, with absolutely no covariances between the two, so that we understand that it's only MODIS that is driving the changing in aerosols. So I'm doing 2 simulations, a control where only weather observations are simulated, and a MODIS assimilation, which is the same that the control, but with the assimilation of MODIS, starting on August 1st after the meteorological assimilation has spun up. So here's for the first 10 days. This is in observation space. So I'm the white is where there's no observations over the 10 days. And you can see at this point, there is fires in Oregon that shows higher AOD that were predicted by FIN. And that there is actually a larger plume shown by MODIS that seems to be due to the same fires, but lower AOD over the source region, at least seen by MODIS. So when you compare the two, so observation minus model, we can see that the actual source region was overestimated and the plume was underestimated. And after assimilation, this is the beginning here, starting from the same initial conditions, some of that biases has been reduced by increasing the emissions or increasing the aerosols close to the source. But then what is with CAM-CAM, you can look at AOD according to the different sources. And you can see that those biomass burning sources are mainly in the form of BC, POM, and SOA that contributes a lot to the signal of the total AOD. While the sulfates are important in the south and east, together with the SOA from the biogenic sources in August, that can be seen in the total AOD. So now if we look at the change between the MODIS assimilation run and the control run, you can see that those differences are going in the right direction, where BC and POM are updated, but in one direction, and the sulfates are updated in another direction, and T-salt in another direction too. So you don't increase artificially the sulfates in Oregon because you're seeing a fire. That's because the signal is very clear from the film emissions.
2 minutes.
Yeah. So then we're getting into closer to the next 10 days of simulation is getting closer to the fires we're interested in Washington State. And interestingly, we are seeing similar behavior where the observations over the fires suggest an underestimation there. But then over Oregon, the bias has then completely disappeared, which is probably due to the emissions update, which is a good thing. And then for that same period, we're kind of seeing the same thing where the plume is not very well constrained until it reaches the East Coast in this case, and an overestimation of the Washington source that is developing at this point. So first MODIS assimilation with very standard setup, no tuning at all, is performing reasonably well so far. And the emission update seems to be an important way to improve the forecast and reducing the biases over the source region. But there is, however, something to really dig more, is the inconsistency between the overestimation of the source and the underestimation of the downwind plume. That could be maybe the deposition is overestimated downwind, or it's just a saturation of MODIS over the fire source that is able to see the plume, but not the actual fire, very large emissions. So that's something we need to take into account and make sure if the source is not very well defined by MODIS, we should be able to correct that downwind, because otherwise our emissions estimation is gonna be underestimated. So that we're also gonna add the MOPIT CEO to be able to constrain BC and POM further, and then I'm going to compare with independent measurements, surface PM2.5 and NDAC, that in particular the CO measurements over NCAR that show that the CO plume was measured during that month. So if you have any questions, feel free to email me, or I'll be sticking around a little bit. Thanks.
All right, thank you, Ben. Our final speaker for the session is Simone, who's going to talk about the implementation of karma in CSM2.
Okay, can you see my screen?
Yes.
All right, thank you. And so I'm going to talk about our ongoing work on the integration of the karma model, a size resolving aerosol model, into CSM2. And this work is funded by the NOAA program of the Earth Radiation Budget. And I want to acknowledge my co-authors, Mike Miltz, Winshan Zhu, Francis Witt, and Chuck Bedin, and we're working with Ping-Fei Yu as well on this. So the main goal of the project is to integrate and fully couple a tropospheric stratospheric sectional aerosol model into CESM. And we're using the CARMA framework, which is the Community Aerosol and Radiation Model for the Atmosphere. And this model, as many may not know, is already in CESM and is used in various versions, for instance, with KM4, but also with MAM. And both clouds as well as aerosols can be simulated with this model. And often it is used in parallel to the MAM model. But currently, there is no version that really is a complete replacement between the aerosols. So the MAM aerosols are always running in addition, or the BAM aerosols, but it's not that we have a complete replacement. And here what we really want to do is have the option to switch out to the sectional aerosol model in CESM2. And this work is based on earlier work that Ping-Fei Yu has done in earlier model versions. And so the idea is if we have the sectional model, we can use it to benchmark the modal model in CESM2. We can compare it to observations. This is much more detailed way of representing aerosols. And so that will be an opportunity also for the community to develop further other models in this version. And so we're hoping that this work will eventually be released, hopefully getting into the trunk in this year and also being released in the next version. So another thing is that we're supporting the Musica effort in integrating different aerosol schemes and also supporting eventually different resolutions and dynamical cores, which is not the case at the moment. So what is the difference between a modal and a sectional aerosol model? We are mostly using the MAM scheme in CESM. You can see that on the left. We have 4 modes currently, and we'll see later a talk of a 5th mode that can be added, but it's basically mixed aerosol particles in each of these modes. And since it has a mode description, it is cheaper and it has been used now excessively for climate simulations. But it has shortcomings. It has constraints, fixed modes, and especially for situations like high aerosol loads or other things, it is constrained in these limits and may not be realistic. Then for the sectional model on the right, what we are using here is a model that, as I said, is a full aerosol description. So it describes 2 groups. One is a mixed aerosol group, which contains the organic and black carbon, organic carbon and black carbon as a sulfate, salt, and dust. While the other group is a pure sulfate group that is separate. And both of these groups have 20 bins with a slightly different size distribution. And so having that model will allow us a better representation, movement between the bins of the aerosols. And there are various observations that can be used to compare those size distributions. So we expect that this is a benchmark model, also in terms of radiation and heterogeneous chemistry may be improved. And so what needs to be done, what has been done in the implementation. So since CESM MAM aerosols are coupled to clouds, radiation, and so on, we have to do this also for CARMA. And we try to stay very similar to the framework like what MAM is using. So we're trying to do a similar approach in implementing that will make it easier later to combine those schemes in the Musica version in a more, more modular version of the code. So we're going through radiation and optics. CARMA has a core shell approach assumption with currently lookup tables. We include aerosol cloud interactions, ice nucleation, cloud aerosol interactions in terms of interstitial to cloud-borne movement. Currently, we don't have the heterogeneous freezing included yet, but we have wet and dry deposition, the convective scavenging and evaporation, though there are some slight differences in the setup. And we're working on aqueous phase chemistry, heterogeneous chemistry, and secondary organic aerosols to be included as well. I want to show some preliminary results because right now we are already have results for the stratosphere And what you can see here is a simulation of the Mount Pinatubo eruption, which is a really nice example because you go from very low aerosol loads to very high loading. And so you can nicely use it as a case study. And there are many lines, but if you first look at the dashed lines, this is basically the injection, the SO2 burden, that is the injection right after the Mount Pinatubo. You see that strong peak, and then it is declining because then SO2 is forming sulfate in the stratosphere. And so we're looking at the blue line, which is the MAM model, which is the dashed line underneath those others. They have the same amount. It's a 10 teragram sulfur injection. And then the blue line, the MAM model, shows this following nicely the observations of a peak and then a decline. And these are like high resolution, I think, radar observations of sulfates after Mount Pinatubo. However, if we run KARMA, the first attempt was the same 10 teragrams, we see much lower peak. And then we realized that actually earlier model studies by Jason English, he has excessively used KARMA for those evaluation of Mount Pinatubo, is that actually the more realistic or the more measured amount of injection of sulfur after Mount Pinatubo was like 18 teragrams of sulfur or something around that. So we increased the amount, and then you see a much better representation, at least of the tail of this. And there are always large uncertainties in those observations as well. Many other models actually show a very similar distribution. So KARMA is able to get the same sulfate burden, but needs much more injection than what MAM uses. And that's because of the difference in how MAM is constrained in their range of sigma in forming larger aerosols. So the aerosols don't get as large and they don't fall out as quickly. So this is an AOD plot, and that is the same model simulations again. The blue line is the MAM simulation, and you see the comparison to LIDAR and SAGE, which is very nice. If we do look at our CESM KARMA run with the 10 teragram sulfur, we don't reach those RAD values. However, if we do double or go to 18 teragrams, then we get a much better representation. And there is also the study from Jason English, as I mentioned before, that had a very similar distribution than we have with the 18 teragrams. So there's the point is really uncertain actually how much injection you need to get the same result for after Mount Pinatubo, which is critical if you think about that. For instance, for geoengineering studies, we want to estimate how much sulfur is needed. So that's one thing we're going to look in the future. We also look more, 2 more minutes, or yeah, we look more at evaluation in terms of size distribution. There are some nice balloon data. Laramie Winshen had made this plot comparing size distribution before the eruption, shortly after, and then a year after or so, not quite. But both MAM, which is the lines, and so the dots are the balloon observation. This is number concentration with regard to the radius. And the sulfates, the pure sulfates, are in blue, and the mixed particles are in red. Both actually show very nice agreement with the balloon data. So that's one way to look at these data. Another way is we'll compare to ATOM observation for other periods, for lower loading aerosol cases, and so on. So this is work in progress. And in summary, yeah, we are implementing this version. We have some initial results and still have to evaluate. Already seeing some very interesting results with regard to Mount Pinatubo simulations. And one thing is that we continue to adopt in the future a new transport scheme and new dynamical course that hopefully we can also couple to the Musica version 0 options of regional refined grids. And with that, I stop. Thank you for the attention.
Great. Thanks, Simone. So we've got some time for questions and discussion now till 10:25. So if we want to stay on time, maybe 5-6 minutes. Oh, sorry, 10:35.
Yeah, and then we can take a 10-minute break. So sorry about my last minute changes to the agenda. I left in some typos.
That's fine. No, I didn't catch them from what you posted, so it's everybody's fault. Wow, the chat has a lot of questions. I'm not sure how many have or have not been answered. Just see. Does anyone have anything that they want to discuss from the chat that sort of needs some more open discussion? We have got a lot on multi-scale modeling here, which is certainly one important topic for the week.
Also, Maria is back if there are any
Oh,
open questions for her.
oh, good. Okay.
One thing I want to point out about the higher resolution is that CAM is a hydrostatic model. And so there are definitely limitations going down to 3.5 kilometers. So it may be technically possible to run the regionally refined grid down to 1/16 of a degree in some regions, that not all the physics will probably work well. And so we're looking forward to using CAM with MPAS to handle those much finer resolutions.
This is somewhat related. So I know the numbers for Wacom. This is sort of related because we got questions about computational expense right now, but what's the core hour cost per year for CAM when you're running with regional refinement?
It'll depend on, what the actual grid is. So
Like 8th degree CONUS sort of
for
thing.
the CONUS grid, 150,000 core hours per year, I think. Anyone have something else in mind?
It's around that. I think it was 180 when we ran it, but that was also with a lot of output. So your output changes your computational time as well. And then also the chemical mechanism has an impact. But I think that for a couple proposals, we've calculated it as a kind of a per grid cell indicator, and that seems to scale really well between the different grids. So that may be a number to publish on the wiki, so that for people that are doing the grids can have a rough idea of what the computational cost is.
Yeah, I was going to say that it's the chemical complexity, and then also just, it's not just going to the finer resolution in terms of spatial scale. You really have to drop the time step quite a bit. So it's very hard to keep track sometimes of all these different configurations and what they cost. And I'm guessing if you do like a 1/4 degree, you don't have to do such a big time step cut. So it's good to get those numbers out there so everyone knows, like, yeah, what the burden is to do some of these runs.
Hi, Nick. Just so that the number that I have for CONUS with just CAM, not CAM-CHEM, is about 55 or 60. And so that indicates that the chemistry is doubling the cost. Does that seem reasonable, Forrest and Nick? Yeah, that's very reasonable. Yeah, it's at least doubling. Okay. Woo. That's why
because of the number of compounds to be transported.
Yeah.
Primarily, as well as solving the chemistry, but most of it is the transport.
Yeah, and definitely to echo what Forrest said, if you save a lot of output, that really, like, I found it can almost, like if you save like every time step, because you're really interested in that kind of stuff, could almost double your runtime at these kind of resolutions. So it's a big swing in core hours with all these different choices.
So that's why we're doing a community run at NE30 for 10 years, saving monthly restarts, so that hopefully that'll help people to get started, and they don't have to run a full year. They can run the month or two they're particularly interested in.
Yeah, and especially we also have the LAN spin-up files for that. At least it doesn't have to be consistent for the LAN. It can be a slightly different year. At least that's what we usually do. So that will also help to have that. So the users only have to use an interpolation program to produce their initial condition files. And those runs are, by the way, done. They just have to be announced and still put on the website. But if you already want to know more about it, you can email us.
So maybe Simone, do you want to clarify the cost of karma? I think you've answered it a couple of times.
But I did currently, it seems to be about 3 times as much, even though, yeah, we're having 120 more affected tracers. That is based on a 2-degree ChemChem model version. I'm not sure how that changes when we have like running WebCam or something like that. But I don't expect that it would be different. We'll see. Looking at the chat, there are more questions. So karma, in terms of prescribed partition infraction to different size bins for each species. So yeah, we start with a certain mass, and then it will be fractionally increase with the bin. So the mass bins are the same. It's not the size bins that we're using, but it's kind of mass bins that describes the different 20 bins. And maybe when Chen or Mike can clarify, or Chuck.
Yeah, so for the different emissions, we use the AeroNet observations to assume the size distribution, and then we use that size distribution to do the prescribed partitioning of the emissions into different size bins.
Good. Well, maybe we should take a break, let everybody get up and walk around, and we'll restart at 10:35. And with Ximing, let me, I made a corrected agenda, and hopefully Ximing can finish condensing his 20-minute presentation to 10 minutes. I really apologize about that. So, but then the rest of the agenda is correct. And we'll have some discussion later after that.
Also, yeah, we have like a informal networking hang around period from noon to 1.
Right.
Cool.
So see you all back in 6 minutes.
So hi, Luisa. Could you hear me?
Yes, I can hear you. I can't find all my buttons.
Oh, cool. Okay, good.
Sorry about the confusion.
Oh, no problem at all.
It was a very important talk. Hardly worth 20 minutes, but just to be fair.
So could I share my screen?
Yeah. Yes, please.
Okay. So
And
is Nick
yeah,
take over?
I can share this session.
Great, thanks.
You like? So it's 10:35 here in Colorado. So why don't we restart? And the first speaker of this final section of talks is Ximing Qi from Texas A&M University, talking about the impact of volcanic eruptions on the ice nucleation and its sensitivity to emission scale. And you have 10 minutes with some buffer.
Okay, thank you, Nick. So thank you for this great opportunity to share my recent study about the impact of the volcanic eruptions on the cirrus cloud. This work has been done by Dr. Xiaohong Liu's research group, and we want to thank the help and communication from Simon, Luisa, and Daniel. And also thank the support from the DOE NGD project. Here is the outline of my talk. Firstly, we will look at the current vacuum 6 dust bias in the stratosphere. Then I will introduce the MAM5 and some changes we made in the cirrus cloud ice nucleation. The results part will focus on the improvement of the dust and the changes in the cirrus cloud ice. At the end is the conclusions. The cirrus cloud is very important to the Earth's climate. The model simulated bias about the sulfate and dust aerosols would affect the homogeneous and heterogeneous ice nucleation process in the cirrus cloud. So we see this unexpected dust difference occurred after the Pinatubo eruption. This is the difference between the MAM4 with and without volcano emissions large simulation conducted by vacuum 6. So we see this dust difference in the lower stratosphere and upper troposphere. The similar bias also shown in the geoengineering results after sulfate aerosol released in the stratosphere. So the MAM5 is designed to solve this dust bias. The reason that generates the extra dust in the stratosphere is due to the remaining process between the accumulation and the course mode. This is designed to promote the lifetime of the sulfate aerosol in the stratosphere, particularly after the volcano eruptions. However, this process also includes the dust and the seesaw. The dust lifetime enhanced by this process, and the accumulation mode dust are converted into the course mode dust, which can participate in the cirrus cloud ice nucleation. The MAM5 added another mode to isolate the stratosphere sulfate to treat the stratosphere sulfate in the separately and no longer exchange the dust and the seesaw between the accumulation and the course mode in the atmosphere. Here we show how the aerosol would impact the ice nucleation in the cirrus cloud in current CAM6 ice nucleation scheme. The ice nucleation scheme is based on Liu and Penner 2005 and Liu et al. 2007. This parameterization links ice nucleation with the aerosol number, temperature, and updraft velocity. The Aiken mode number is used to represent the sulfate Aiken mode number to participate in the homogeneous nucleation, and the coarse mode dust number is used to present the dust and participate in the heterogeneous ice nucleation. Also, the accumulation mode and the coarse mode sulfate number directly add into the active ice number in the stratosphere, based on the update in the 2017. So here we use more accurate mass-weighted sulfate number to replace the Aiken mode number for the homogeneous ice nucleation. And then we apply this accumulation and coarse mode sulfate number to directly participate in the ice nucleation, not only in the stratosphere, but also in the troposphere. And here we design for simulations. So the MAM4V is the control run using the current default WACOM configuration. The MAM4NV is the same as MAM4V, but without volcanic emission. The MAM5V is using MAM5 with changes in the ice nucleation scheme. The MAM5NV is the same as the MAM5V, but without volcanic emission. All the simulations are lodged to Mira2 UVT and conducted by the WACOM 6. And the simulation time is from 1990 to the 1994. The biggest volcano eruption during this period is Mountain Pinatubo eruption. Mountain Pinatubo is located at the Philippines and erupted on the June 15th, 1991, and injected 10 teragram SO2 into the stratosphere. That is what we used in the model. Okay, so here we see the results. Firstly, we show the aerosol concentration from 4 simulations. The left curve shows the average in the lower stratosphere, and the right curve shows the average in the upper troposphere. The red means the MAM5 results, while the blue shows the MAM4 results. The dashed line are the run without volcano emission, and the solid line are the runs with volcano emissions. Let's look at the dust results, the first row first. The MAM5 with and without volcano emission shows very close dust concentration in the both regions, suggesting dust bias shown in the MAM4 has been improved. Meanwhile, we see the MAM5 has little impact on the SO4 concentration compared to the MAM4. So with the less dust bias in the lower stratosphere and upper troposphere, we can evaluate the impact of the volcano eruptions on the cirrus cloud by comparing the results between MAM5V and MAM5NV. Okay, here we see the results from the heterogeneous ice nucleation first. The left panel shows the relative difference of the coarse dust lumber concentration in 1992. That is between MAM5V and MAM5NV. 1992 is the year after Pinatubo eruption. The red and the yellow boxes are shown in the middle and the right panel. There is no difference between the two simulations as we expected. I mean, no significant difference. And then, therefore, we see no clear difference in the heterogeneous ice nucleation between these two simulations, as there is no dust difference. Now we look at the sulfate aerosol number in the different modes. The first row shows the difference in the Aiken mode. The left panel is the difference in 1992, a year after Pinatubo eruption. Surprisingly, we see the sulfate aerosol Aiken mode number decrease in 1992 almost everywhere in the atmosphere, but more in intense in the stratosphere. And we also see the time series. This is lower stratosphere, and this is upper troposphere. We see this eigenmode number for the run with the volcano emissions. That eigenmode number increase initially, but several months later, it decrease sharply and lower than the run without volcano emissions. And this decrease will last for years unless another volcano erupt at the end of 1994. So this is for the eigenmode number. But for the cosmode number, we see a different story. We see this cosmode surface number increase after the Pinatubo eruptions and keep several fold higher than the runs without volcano emissions. So here we see the homogeneous ice number relative difference. The left panel displays the volcano emission enhanced homogeneous nucleation in 1992. The middle panel and the right panel shows the enhancement lasts for years. This means the increment of the surface aerosol number in the accumulation and the coarse mode overcomes the number reduction in the eigenmode. As the coarse and the accumulation mode number can have higher potential to participate in the ice nucleation. The second row shows a total cloud ice number averaged in gray box. As there is no significant changes in the heterogeneous ice nucleation as we showed previously, so the homogeneous ice nucleation dominate the change and promote the overall cloud ice number. Here we show the cloud forcing. So first we show the table is the man5V minus man5NV. That is long wave cloud forcing in 5 years. And here we show is the man4V minus man4NV. That also long wave cloud forcing in the same 5 years. As we expected, in 1990, there is no difference of the long wave cloud forcing as there is no significant volcano eruptions. But in 1991 and 1992, we see the man5 shows bigger long wave cloud forcing difference because the promoted the cirrus cloud coverage, as we showed previously. But we see there is no difference in the man4 simulations as the dust contamination and also the impact from the eigenmode surface reduction and use the old ice nucleation scheme. So here's my conclusions. man5 improves the dust bias in the lower stratosphere and upper troposphere. The mountain Pinatubo eruption increased the accumulation and cosmode surface aerosol number, but decreased the eigenmode number for years after the eruption. Through enhancing the homogeneous ice nucleation, the mountain Pinatubo eruption promoted the cirrus cloud ice number concentration and increased the long wave cloud forcing by 0.3 watt per square meter globally for 2 to 3 years. Yeah. Thank you. That's all for my presentation.
All right. Thank you, Ziming, and thanks for last minute shortening of your talk. We appreciate that. So let's move on to the next presentation, which will be given by Yongqing Zhu from NCAR, and it's persisting volcanic ash particles impact stratospheric SO2 lifetime and aerosol optical properties.
Hello, everyone. Today I will talk about the impact of the volcanic eruptions on the stratosphere chemistry and aerosols. I changed the title slightly, but the content is the same. Okay, so volcanic ash is usually neglected in the climate simulation because ash are considered large high density particles and fall fast during the in a few days or weeks. Okay, however, this is actually not the case. So many observations after big eruptions reported that 8 months or a year after those eruptions, they observe the ash-coated sulfate-coated ash particles with odd shapes in the stratosphere. So those motivate us to look into some volcanic eruptions with ash, and we picked the 2014 Mount Calude eruption. Of the Calypso reported by Vanier 2016 sees that the volcanic aerosol layers persist more than a month. And you can say that maybe those are sulfate particles, because sulfate usually persists pretty long after the eruption. However, from a depolarization channel from Calypso, it sees those particles are actually odd-shaped, not round like sulfate. So those are actually persistent ash particles. Then we may wonder, how could those ash particles persist so long? Is it because they are very small, like submicron sized sulfate? And we have some very valuable data from ATRACS that observed supermicron sized particles from the Mount Calude eruption a month after the eruption. So this figure shows ATRACS size distribution captures a lot of particles that's supermicron sized. And if we only simulate the pure sulfate, it cannot reproduce the size distribution. And then we add the ash particles in the model, and we assuming a 2.3 gram per cubic centimeter for the density, which is similar to volcanic glass that many other models used. However, we still miss a lot of particles that's larger than 5 microns. And then we switch the density of ash particle from 2.3 to 0.5, and actually we reproduce the size distribution very well. And those particles are not volcanic glass, and it's like pumice with parallel structures. So to answer the first question, so those persistent ash particles are actually micron-sized with a density close to pumice. And then another interesting point of our research is about the lifetime of SO2. So our the modeling community, or at least me, I always think the lifetime of SO2 is about a month. However, Karn et al. 2016 have this chart on the left, showing on the left side, showing that the SO2 lifetime varies from like less than a day to 14 days, depending on the injection altitude and the mass of the injection of the volcanic eruption. So we look into the Calude case, and then to compare the observed SO2 lifetime with the model. The black line here shows the vacuum case that the SO2 can react with OH, and OH is get depleted very rapidly in the plume because lots of SO2 get injected. The lifetime is 26 days. However, the observation says the lifetime is only 7 days. Why is they are so different? So one of the reasons is that the observation have the noise. So we subtract the SO2 that's below the ohmie detection limit, and it actually reduces the observed reduce the modeled SO2 lifetime to 13 days, getting closer, but still. And then we tried many other methods to reduce this lifetime, but nothing worked really well. And finally, we find some lab experiment that says a heterogeneous reaction of SO2 on ash particles happening. When we apply this reaction in the model, it's actually explain the remaining discrepancy. So this reaction, I have a very brief chart here. It's complicated. Basically it means like on the mineral surface, such as ash or mineral dust, SO2 can irreversibly react to form the sulfate. So first we have the SO2 and we have this mineral particle, and through a process called adsorption, and the SO2 can quickly stick on the surface of the mineral ash with no barrier. And so unlike the nucleation, take quite some energy. And then those SO2 get oxidized into the sulfate. But however, as long as all the available sites are taken, the reactions stop. So unlike the growth, so this reaction only form a film on the surface of the particle. So in conclusion here, that none of the observations in the model get the SO2 correct. So the actual SO2 lifetime is 17 days. And at the end, this figure shows that the ash particle can impact the sulfate burden in the stratosphere. Here's a case with no ash injections in blue, and then we considered ash injection, but it doesn't interact with the sulfate through the heterogeneous reaction. And then we have the case in red that adding the SO2 heterogeneous reaction on ash. And adding this reaction results in 50% more of sulfate removal within 60 days. Okay, so in summary, this work is conducted in WACM4 karma model. So in summary, we have to modify the diagram of physics and chemical process in the volcanic clouds. So in a typical model that the volcanic eruptions erupted gas, SO2 and ash in the model. And however, the ash can sediment very quickly, so it is usually neglected in a climate simulation. So the simulation only consider the SO2 react with OH and form the sulfate aerosol. However, our study says we can also consider the ash and react with the SO2 and form the mixed aerosol. And those aerosols can also react with a pure sulfate. So large ash sediments with sulfate take part of the sulfate away from the stratosphere. Small ash micron-sized particles with sulfate can persist longer and impact the climate in a longer term. Yeah, thank you. And this is an article we published, and you're welcome to take a look. All right.
All right. Thank you, and thanks for sticking to the time there. So next talk will be given by Michael Weimer from MIT, and the title is Towards Gravity Wave Aware Chemistry in WACM.
Okay, thank you, Nick. I'm a postdoc in Susan Solomon's group, and first of all, I want to thank all the co-authors that enable this work. And we are interested in on how small-scale gravity waves impact the chemistry in vacuum. And we know from it might be. We know from observations that we know from observations that that small-scale gravity waves can lead to temperature perturbations up to 15 Kelvin in the stratosphere. But we also know that the chemistry non-linearly depends on the temperature. For example, polar stratospheric clouds exist only below a specific temperature threshold, and reaction rate constants themselves depend exponentially on the temperature. So small perturbations of the temperature can lead to a different chemistry in the model, and this is what we want to investigate. But of course, these small-scale gravity waves are not resolved by the model. But we have the gravity wave parameterization in the model that treats these small-scale gravity waves, but they are currently not coupled with the chemistry in the model, and this is exactly where the idea of our project comes in, because we can get vertical displacements of the gravity waves or of air parcels in the gravity wave and the vertical gradient of the temperature, transfer it to the chemistry, and then get a temperature perturbation due to the gravity waves according to this formula, which comes from linearized theory of gravity waves. So this is kind of the amplitude of the gravity wave temperature perturbation, and we apply this then as a subcycling approach for the chemistry, which you can see here on the right-hand side. T prime is the amplitude of the sine wave, and we sample this sine wave at, for example, 10 points to get a good representation of the temperature perturbation due to gravity waves in the chemistry. What we then did as first test simulations, we used vacuum SD, the SD version of vacuum relaxed to MERA2. We simulated time period from 2010 to 2011, and we conducted 2 simulations, one without the subcycling approach and the second one with this gravity wave parameterization included. And currently we implemented it only for orographic gravity waves because this is kind of easier to implement. And on the right-hand side, you can see the distribution of these T prime values. And you can actually see the distribution of the mountains in the model quite well, and especially at hotspots like the Andes, there are quite high values of T prime, and also at the Antarctic Peninsula. And you can also see that the magnitude of these T prime values is comparable to what we expect from measurements, which is quite promising. But of course, we have to evaluate our T prime values first. And here's a first comparison from Catherine Wilcar's PhD thesis, who graduated this year. Here she compared the vacuum distribution of T prime values with the cosmic T prime values, which looks quite good in the summer months. Here is shown for the Andes for January. But if we go to winter, our algorithm actually didn't really work, and we have to adapt our algorithm to derive T prime for cosmic. So this is ongoing work, and in the future we also want to look into AS data, because AS is able to detect longer vertical wavelengths. And the whole question is, do we have to scale our T prime values, especially for higher altitudes, as it is done for the momentum flux in the gravity waves? We further looked into in the comparisons of the chemical substances with observations. And here it's shown for MLS. You can see here a time series for a specific point where you can see that these peaks in ClO, which is an indicator of chlorine activation, is quite good represented in both simulations. But in the simulation with gravity waves, which is the blue one, you can actually see that these peaks are actually improved due to our new parameterization of including P prime, which is a quite promising result. But we have to further look into this, of course. Here you can see the relative differences between the two simulations, the simulation with the subcycling approach and the simulation, the reference simulations for the tropics and the high latitudes. And you can see that there are quite large relative differences in the tropical tropopause region, where we expect cirrus clouds to exist. So this is a region where we expect that heterogeneous chemistry is active, and where we could expect that also this difference could come from. Also, of course, we see differences in the southern high latitudes. Here it's shown for September 2011. You can see that at the edge of the polar vortex, there are some large relative differences. But you might know that the chemistry is one of the most expensive parts of the model. And actually, if we use this 10 times subcycling of the chemistry, it actually uses twice the time we usually use in WACM. So we are currently also thinking about approaches how to get similar results with fewer subcycles. And we came to the result that if we use sine wave distributed random T primes, we can actually use only 3 subcycles to get the same result as for the time sampling approach I mentioned. And this is basically shown here for ClO. On the x-axis, the differences of the 10 times subcycling to the reference is shown, and on the y-axis, the same is shown for the random approach here. And you can see that they are quite similar in especially these large differences here. Color-coded is the pressure, and this is exactly the pressure range where the heterogeneous chemistry is active. So this is a really promising result that you can actually use only 3 subcycles instead of 10 to get similar results using our T prime parameterization. So to summarize, we implemented the method currently for orographic gravity waves only. We, of course, are planning also to include non-orographic gravity waves. We did first comparisons to measurements, but we have to look into that a bit further. And I showed that using sine wave distributed random T primes lead to a similar response with only 3 subcyclings. So this is quite promising. And of course, in the future, we want to compare our results with cosmic and airs data. And in the farther future, we want to do multi-year ensemble simulations with and without T prime to see the impact on the ozone chemistry. And with that, I thank everyone for listening, and I'm happy to answer any questions.
Thank you. There is a quick question in the chat. Maybe you can answer there, or we can answer at the end of the Q&A period. So we'll move on to the next presentation, which is given by Jaga Richter from NCAR. And the title is Small Ensemble of Climate Intervention Simulations Using Stratospheric Aerosols.
Good morning. My name is Jaga Richter, and I'm going to present work that's collaborative effort with several from Cornell University, Danielle Vigioni, Doug McMartin, Walker Lee, Sally Woodhouse, and several people in CGD who have helped either setting up simulations or giving input to their design. So yeah, as Nick mentioned, I'll talk about a small ensemble of climate intervention simulations using stratospheric aerosols. And the reason we do this research is that climate intervention could potentially reduce the worst consequences of climate change. The stratospheric aerosol injection, or SAI, seems to be the most promising, or you can say most studied strategy. Marine cloud brightening is another strategy, but there have not been very many recent global studies of that. So SAI looks most promising for now. However, there still exist very large uncertainties in the impacts of SAI. So back in 2016 and 17, Simona Tilms led the effort of the Geoengineering Large Ensemble, or GLENS, which was the first large ensemble carried out with a single model with 20 ensemble members, which had strategically placed SO2 injections at 15 south, 15 north, 30 south, at 30 north. And what I mean by strategically placed is that there is an algorithm in the model that would decide every year where to put those injections, and it would put them in such that the global mean temperature, the north-south gradient, and the pole-to-pole gradient will remain roughly at 2020 levels. So we're trying to get the climate as close to present day as possible. And in that work on GLENS, we use CSM1, WACM5, and only with middle atmospheric chemistry. So there was limited potential for evaluating tropospheric chemistry impacts that was just not available. And GLENS was run with a very high emission scenario, so RCP 8.5 to 2100, with a start in 2020. And injections were also at a relatively high altitude of 23, 25 kilometer, which is really hard for the current technologies to reach. And Simona has done additional similar simulations similar to GLENS with CSM to WACM6. And they had very similar setup, except now she was using SSP's 585 and the overshoot scenario, but also start in 2020 and injections at these high altitudes. So I'm going to present to you just the simulations we are running now, which are complementary to GLENS and the simulations done by Simona. And they're designed to be a little bit more realistic. So we start intervention in 2035. And why 2035? This is on average where most models show that we go over the 1.5 degree threshold. And that is kind of normalizing for where we are right now. So if you normalize to the WACM's pre-industrial temperatures, we would reach 1.5 degrees in 2025, which we know is not true because we're already at 2021 and we got a little bit of ways to go. So most IPCC models show it going over roughly around 2030, a little bit later, and we start the intervention a little bit after that. We're also focusing on a moderate emission scenario, hoping that there will be more efforts to mitigate emissions so we wouldn't have to offset such a huge warming. And we lower the injection altitude to 21 kilometers because there is research done on how high sulfate could be carried into the stratosphere, and that currently could be achieved with the aircrafts that exist or could be easily built. And we also capped the simulations at 2069. Again, with past 2069, it is so hard to tell what the emissions will be. And we want to just keep focus on the shorter term impacts, which would give us a lower signal to noise, which you may say, well, is bad for doing research. However, if there is a small signal from geoengineering for doing it a mild configuration of that, we want to find it out and we want to give, again, a realistic evaluation what the impacts might be. If you're just looking at the period of 2080 to 2100, yes, the signal to noise is much higher, but that is also not a very realistic implementation of geoengineering likely. So we've completed 5 ensemble members of these simulations, and 5 more members will be carried out this summer, really as soon as we manage to archive and convert the first 5 into time series and move them off scratch. And also we will carry out 5 more ensemble members of the control, so of the SSP 245 just from 2020 to 2039. And we'll add some additional high frequency output. And I'm not sure if you realized it, in all the CMIP6 simulations, the daily Tmin and daily Tmax are not correct. So they're all show the daily average. So we don't have information to really do analysis of extreme weather, etc. So we will rerun a subset of those simulations. And that's coming out of an NSC allocation. Okay, so finally some figures on these in comparison to Glenn's and the runs done by Simona. So in our new simulations, the injections are primarily going at 15 south and a little bit at 15 north and other locations, but there is a huge dominance of 15 south injections. This is in contrast to Glenn's, in which the algorithm was picking injections primarily at 30 north and 30 south. And in Simona's simulations, the injections were going primarily in 30 south. And this is where the injections go is really not fully understood. It depends obviously on how much the surface temperatures depart from the goal. And then the algorithm is picking the best injection to meet that goal, but it's not something that we fully understand just because of the complexities of the system. And I'll talk a little bit about it. And there is differences between CSM1 and CSM2, like in the AMOC, that are contributing to the model picking more southern hemisphere, but it's not exactly clear why it would pick more at 15 south versus 30 south, for example, between these two sets of runs that are quite similar. Okay. So here are the zonal mean temperature changes when you inject these quite large amounts of aerosols. In these bottom panels, I'm showing the period of 2050 to 2069 relative to our control of 2020 to 2039. And you get about 4.5 degrees of stratospheric warming. And that is kind of comparable to what we had in Glenn's in an earlier time period of 2040 to 2059. Again, by the end of the century in Glenn's, our stratospheric heating was twice of what we have right now at the end of our simulations. And if you notice, there is a little bit of warming in the southern hemisphere, which will become important for when we look at the surface impacts. So here's a similar figure, but looking at zonal mean wind. So if you change the temperature structure near the equator in the stratosphere by thermal wind balance, you expect the winds to be changed as well. So specifically in DJF, we anticipate a strengthening of the northern hemisphere polar vortex. And we saw this in Glenn's as well. And however, in the tropics, the responses are a little bit more complicated. So in Glenn's, and this was in a paper by Amy Butler and others from NOAA, there was a decrease overall of tropical winds. And you can see this horseshoe shape reaching down into the upper stratosphere and even into the lower troposphere. But we do not see the same thing in the new simulations. Actually, you see the speeding up of the winds a little bit close to 30 south and 30 north. And why is that different? And again, it comes down to where the injections are going. So on this plot on the right, I showed just single point injection results from our very old simulations with CSM1, which show that if you inject just in 15 south, you do not necessarily get the decrease of winds across the entire tropical region. The response is a little bit more mixed. So that's what we're seeing in DJF in our new simulations, that mainly relates to where the aerosols are going. And also, though, you see this in the changes in the QBO. So if you place your injections at the equator, there have been several studies that have shown the QBO will get shut down. However, this didn't happen in Glenn's because the injections were going in 30 south and 30 north. So even by the end of the century in Glenn's, the QBO remained with a period of about 20 months. And in Simona's simulations, it's about at 16 months. Whereas in these new simulations, we go to a QBO that's super fast, that has a period of 13 months. And that's very different from what it does in just an SSP 245 scenario. So lots of details of injection matter. And if they matter to the stratosphere, then I can tell you they'll matter to the surface. So what I have here on the right-hand side is Glenn's. So this is first RCP 8.5 changes, so warming everywhere. And if you look at our geoengineering simulations relative to control, that the dominant feature was this winter warming over northern Eurasia. And so we thought that there's pretty a persistent feature of this geoengineering strategy when you get this large tropical heating. However, that is not the case in the new simulations. On this plot here, I'm showing the 2050 to 2069 temperatures relative to our control. And you see the key feature is, you can call it a warming hole or a cooling hole. In any case, the primary feature is that you get a lot of cooling over the ocean here, over the Labrador Sea, which is largely attributed to the changes in AMOC between CSM1, CSM2. And you're seeing a little bit of cooling over the northern continents, but you are not seeing this warming. And so here's a DJF just for the same comparison. So you see the patterns in Glens and you see the patterns in CSM2, they are not the same. And here briefly, I'm just showing you the AMOC. So in CSM1, this is a figure from Aishu Hu. If you look at all the RCP scenarios, in all of them, the AMOC is rapidly slowing down, especially in the RCP 8.5 scenario. However, for the more moderate scenarios, the AMOC does not decline as fast. However, in CSM2, if you look at all the SSPs, the AMOC is really decreasing fast for all of them. It's really nosediving. And in Glens, we were able to recover the AMOC with geoengineering, this blue line here compared to RCP 8.5, and it is just not happening in the new simulations. And Simona has shown that also in her simulations, there is the recovery of AMOC in Glens, and there is no recovery of, or maybe somewhat of a recovery in the simulations that she has done. But there is a huge difference between CSM1 and CSM2. So anyway, in short, we're carrying out the small ensemble of climate intervention simulations that are set up to design to be realistic, but really they need to be just taken. We need to look at these simulations and Simona's simulations and Glenn's together and just see what the impacts are and why they're happening, and really understand the key features of where the injections are going and what is driving the impacts. And since many impacts already are showing differences from Glenn's, it shows you that the injection strategy is very important. And depending on what you do with your injections, then you're going to have very different impacts. So anyways, I'll stop here and take any questions.
Thank you, Yaga. We move on to the next talk, which will be given by Doug Kinnison from NCAR. And it is evaluation of the CCMI WMO Ref D1 WACM 6 simulation.
Okay. Can you see my simulation or my my PowerPoint?
Yes, we see your whole screen.
Okay, how's that?
Yeah, looks good.
Okay. Okay, today I'm going to talk about the evaluation of the CCMI, WMO, Ref D1 and Ref D2 simulations, and I'll go into some details on that in a minute. But first, I really want to thank everybody that's been involved in developing CSM2 WACM 6, and it really does take a village to get all this stuff done, and there are a lot of people that have contributed. Let's see. Okay, so these new simulations, these Ref D1s and these Ref D2s are aimed at supporting the WMO scientific assessment of ozone depletion. The next report will be due in 2022. Simulations are going on right now by the community. Some of them are done. When possible, we're going to be using some of the CMIP6 model results that have been already released, and some of it has been published. But there's also these new simulations that Spark CCMI has put together for the WMO. And one is a hindcast simulation from 1960 to 2018, and it's designated as the Ref D1. And this simulation will use the nudge QBO, and it'll also be used to grade the model processes, the dynamics, transport, and chemistry. And then the second simulation, Ref D2, is a new forecast simulation going from 2015 to 2100. And this will be based on the SSP 245, but it'll have a different halogen recovery scenario, one that's more current than what was used in CMIP 6 and which was published in the WMO 2018 assessment. The overall goal, and I don't know if we're going to be successful in the time frame we have left, is that papers will be written on the REFD1 and results will be used from that to weight the REFD2 models results to, say, for example, an ozone recovery. And only the models that do a better job with dynamics, transport, and chemistry will be part of the multi-model mean. Now, for this talk, I'm going to talk about 5 different simulations. I'll show specified dynamics was using MERA. Essentially what we're doing here is we're going from most constrained to most interactive. The REFD1, which is got an observed ocean interactive dynamics, but has a nudge QBO, and it uses WMO halogens at the end of the assessment there around 2015 to 2018. The AMIP simulations were in the CMIP 6 assessment, and they have an interactive QBO that Yaga and Rolando worked on and have published. The coupled simulation is the same as the AMIP, except it has a deep ocean, interactive ocean. And then finally, the REFD2, which is similar to the coupled simulation, except it uses the different halogen recovery. So I'm going to go quickly through some results, and then I'll be done here. So if you first want to look at just the QBO, on the left is what was published in the Gettleman et al. Paper. You see the era of the data on the top, the AMIP, and then the couple below. And you see one deficiency in the interactive QBO is that the westerlies don't extend down to 100 hectopascals. So this is one reason that we wanted for Spark CCMI and for WMO to use the nudge QBOs. We know that we could do a better job representing the QBO. And you see that on the right, again, compared to the era data at the westerlies do extend down. And also, if you want to compare to satellite data, you can align the QBOs with the data. We also took a look, this is work Rolando Garcia did, to look at the REFD1s to make sure that the temperatures are correct in the polar region. These are polar cap averages. The top is WACM 6 REFD1, the middle is a MERA simulation, and then the difference. And where the arrow is going over to the right, you're seeing that in the lower stratosphere, these line plots are at 85 hectopascals. We do a really good job of getting the temperature right, and within plus or minus 1 degree. And you have to, in our current chemistry setup, it's really sensitive chemistry. And if you don't do that, you're going to get too much depletion or too little. And last week, Bill Randall sent me this figure. He and postdoc John Starr have been working on looking at temperature evolution, anomalous temperature evolution. And what they are using, of course, comparing to the stratospheric sounding unit and the microwave sounding unit. Bill published a paper on this for WACM 4 in his 2017 paper, and he's now updated this for the REFD1. And frankly, we do a really excellent job of getting the apparent trend and also representation of volcanic influences. And then included in this is the effect of ozone depletion and greenhouse gases that have on these trends. So I will look forward to them furthering this analysis, but it really looks good. It's probably one of the best representations of the temperature trends. All right, so how about total column ozone? Because this is a big issue for the assessment. I'm first going to show you on the left the polar, on the right the equatorial ozone. The SBUV mod or merged ozone data set is observations, and then this is specified dynamics using MERA2 to nudge. And you can see with the MERA2, good temperatures, decent circulation, we get a very good representation of the chemistry, specifically for total column ozone in the polar region for October, and also in the tropics, which is an annual average at between 20 south and 20 north. If you now add in the REFD1, these are 4 realizations. Little dots are the realizations, and then the solid lines, the mean. You don't expect the REFD1 to match up for every big depletion period. It's not. You might have a cold year in the REFD1 where it wasn't in the observations. However, you see that the means pretty much match up. So there's no apparent bias between running the REFD1 and comparing to observations or what was used in SD. But what you do see in the tropics is there's less total column ozone than what is in the observations and in the SD, and I'll come back to that. Now, if you add in the AMIP simulations, now the difference between the RefD1 and the AMIP again is one is an interactive QBO and one isn't. And there really is no difference in the polar region, and there really isn't no difference in the tropics either. I was curious if that would have any effect on total column ozone, and it doesn't. And so evidently that where the deficiency in the QBO is apparent in the lower stratosphere in the tropics, it doesn't affect the total column ozone. Now, if you add in the coupled simulation, interactive ocean, interactive QBO, again, there's no apparent bias in the polar region. The variability is similar to what you see in observations in the SD, and so everything's looking really good. This is probably some of the best total column ozone we've ever used or derived in WACM. But then you see on the right in the tropics that the coupled system has less total column ozone, even more so than the AMIP. And so why is this? And we talked about this a little bit in the Gelman et al. Paper. And if you look at the vertical velocities as derived using the TEM diagnostics or W star, what you see in the lower stratosphere here, the blue is the fastest, then the RefD1 and the AMIP are pretty similar, and then the SD is the slowest. And the idea here is that if you have faster circulation, lower stratosphere, where the total column is going to be most sensitive, you're going to be bringing up tropospheric air, which has lower ozone abundance, et cetera. And so this all kind of makes sense. We haven't really looked into what the wave properties are changing between the coupled simulation and these other ones yet, and that's something that we still need to do. All right, and just to finish up, I wanted to show the forecast simulations. We're currently running these. This is just the polar region. The RefD2 is the red lines there, and I have 3 realizations, but they're only through 2056 as far as the mean is concerned. And the green is what you would get with the SSP 245 from CMIP6, or 4 realizations there. And the RefD2 started off of the blue or the coupled simulations. And at this point, it's really hard to see that there's going to be any difference in the return date to, say, 1980 conditions. The variability is just very large in these models. And in order to really see the effect of changes in the forcing of organic chlorine and bromine that eventually gets turned into inorganics, you really have to run a lot of ensemble members. And this will come out if you have, say, 15 CCMs running 3 realizations, and when you finally create this multi-model mean, you will see a return date that's different, and it should follow the forcing of the equivalent effect of stratospheric chlorine. So that being said, I think everything's good. Oops, I keep hitting the wrong button. So this was just basically a first look at the RefD1 and the RefD2 simulations, and the results look very promising. And I just want to let the community know, if you're interested in these simulations, please let me know, because the more eyes on this stuff, the better. And if you want to use them for your research, that would be great. So I'll end there, and I think that's it. Thank you.
Thanks, Doug. So we do have time for any questions or discussion on the last few presentations. There were several questions in the chat, but I think all of those were answered. If not, and anyone wants to clarify anything they asked or their question was not answered, please speak up. All right, I guess everyone's questions are answered. Go ahead, Dan. You raise your hand.
Yeah, just interested in this idea about the implementing gravity wave effects on chemistry. I think this is an area, a really interesting area that we could coordinate some activities. At the University of Leeds, we have a NERC project looking at the subscale transport in the MLT, bringing NOx, impacts on NOx and metal layers in the MLT, and how we are doing something quite similar. We're taking the gravity wave spectra that are not have yet to dissipate or be dissipated in the code, so they haven't reached the breaking level. And we're using that information to try and derive some kind of additional vertical transport. And that impacts things like temperatures as well. So I think maybe at the next gravity wave meeting, a future WACM meeting, we can kind of give an update to the group and maybe see if there's some overlap there.
That sounds really interesting. I think it would be great to keep in contact.
Okay, yeah, we'll try and fully, let's schedule a meeting and try and get people talking. That'd be great. It's also with Chet Gardner and at the University of Illinois. So it's a NSF NERC funded grant.
And on a similar topic of the gravity waves, Nick Davis had a comment in the chat or question. I don't know, Nick, if you want to just read it or.
Yeah, sure. I mean, we're doing these regionally refined simulations here with WACM, and so like, I mean, if you're also just interested in general in output or anything, there's no pressure, but it's kind of like I think we're happy to point people to where some of this stuff is, because there's probably an infinite array right now of things people can look at in these runs, and we're really just trying to get a good grapple on what's going on, because when we get down to 10-kilometer resolution, we are resolving a good chunk of the gravity wave spectrum right now in the model. So yeah, the data volume of these runs is difficult to work with, but like it's basically just sitting around waiting for people to use right now. So we've got like 10-kilometer resolve output chemistry and dynamics at like 4-minute time resolution. So you can really exactly see what the waves are doing. It's just, obviously that means for like a year-long simulation, that's just too much for a few people to look through. So if that's of interest to you or anybody else here, let us know.
And Nick, it's going to be huge. I think we're going to, I mean, it may not be practical for, most simulations, but we're going to learn a lot, I think, of the small scale interactions from those simulations.
Yeah, and we're doing, I should say, like, we're not just sort of running the model like we normally do. Like, I'm working on one now where we're actually just disabling all the parameterizations for gravity waves in the refined regions so that we can sort of get an unambiguous answer of like what exactly is going on from what we're resolving, in this high resolution area. But yeah, this is definitely a case where it's like, it takes a while to get yourself set up with like processing output, because you definitely need to make use of like, some nodes to work through all that data.
Nick, do you think it would be better to, I know we're leveraging the CONUS grid and that kind of thing, but do you think it would be actually better to think about a more idealized, smaller grid, park it somewhere like, I don't know, mid-latitudes over an ocean even or something, and just get an idea about, where, if you did turn off the gravity waves, it wouldn't really impact the global circulation, but you'd really at least get to see what's going on in the vertical quite easily, with the data volumes being a bit less.
Yeah, that's one option. You could choose the Southern Ocean and just refine a chunk of the ocean, and then you could slide the refinement and suddenly refine the Andes or something, right? You could really get the two extremes going there.
Yeah, and I know there was some discussion about, because I wanted to put higher res over the poles, and that the gridding software was kind of a little tricky to when you get near the poles, and that there was some talk about saying, well, look, you just have a square, and I'm just going to move that pole, move that to be centered somewhere, so that once you set up that one grid, you're just free to then just go easily move it somewhere else, do another simulation, move it somewhere else, and kind of without necessarily having to go through a lot of this process of setting up a new grid and all that kind of stuff. So I think something a bit more general and smaller scale might be easier to kind of probe these questions.
So Dan, do you think it would be an issue in terms of sort of oblique propagation? If the grid is too small, then anything that passes sort of somewhat horizontally could pass out of the grid.
Yeah, I think Yaga knows kind of like the angle, or has pictures of the angles of what these things are coming up. So as long as it was, not obviously not 100 kilometers square, but maybe something 500 kilometers, maybe. I don't know what that sort of angle is at which you would expect a wave. I mean, I've seen some of when Hanley did his early simulations at 1/4 degree, you could see those sort of waves emanating out, right? So I guess we kind of want to have that. But even then, I still think you'd learn something from just focusing on the vertical effects. Gaga, do you remember? What is that? What of a typical from a front? I mean, how far away does it propagate away?
In real life or in a model?
Wait, there's a difference?
Yeah, well, in a model, it just nothing propagates away, but I think in real life, they could go quite a few grid boxes.
No, we're talking about resolve waves in the model, right? So we're talking about going to higher res and resolving these waves. So I know that the parameterized waves are just in a single column, but like how far away would you have to go to get the biggest effect? I mean, is it 1,000 kilometers? You need a box of 1,000 kilometers to get that?
I think just looking from when I've just looked at maps of the CONUS grid, easily 1,000 kilometers I've seen enough wave packets on that kind of scale. So I think 100 kilometers would be too probably small, I think.
But even that is only a 10 by 10 current resolution grid, right? Originally defined area. It's 100 kilometers for the standard 1 degree box. So you're just talking about sectioning out a 10 by 10 grid or something like that. Of course, you're going to need to, bring that down to the right scale over several boxes. But I think it might be, a more generic box that could be slid around. I guess then it's the hard part is getting all of the tools to do all the, the surface stuff. But
I mean, just remember too, though, like no matter how small you make the refinement, you still have to run globally with the high time step. So
yeah.
Like I know in terms of storage, you save a lot, but the model cost is still going to basically be the same. Whatever you choose for the refinement factor is really going to set a lot of the cost just off the bat, no matter how small it is.
Nick, I think it would be awesome to compare the gravity wave amplitudes that you're getting in this version with what we get out of the parameterization. I mean, I would think that would be of interest from a dynamical point of view too, but we'd be happy to look at those T primes and think about what that means with you.
Yeah, sure. We can include you in whenever we have some of these targeted discussions. I think probably we're going to do some longer runs soon. We're just sort of feeling out with some short runs, like what we can and cannot do in terms of the analysis and, you know, turning parameterizations on and off. But yeah, happy to include you in that.
So maybe we should move on to some more general discussion. We didn't have a lot of formal items that we wanted to discuss, but we're hoping that this is a time for getting feedback on things that you think are missing in the model, what you would like to see, such as I'll just put our few little bullets in the chat there. So, you know, as always, the model is evolving, and there probably will be a release of CESM 2.3 in the fall. It's a chance for you to request comp sets, other features, and we'd also like to hear about your research interests, and what are maybe some of the model development's needs for addressing those topics. And we'd really like to hear how people are using the model, or think what is missing, or are doing any developments that we haven't heard about yet today. Julio has his hand up.
Yeah, I think I got it up a little too late. I just wanted to make one more comment on the gravity waves, if that's all right.
Oh, quite all right. Yes.
Yeah, I just wanted to point out to people that there's an effort being led by Joan Alexander and Chris Cruz, who's, I think, on this telecon, is working on it a lot. It's to look at high resolution simulations using WRF and other kind of high resolution non-hydrostatic models around the southern tip of the Andes, and they're comparing with AIR's satellite observations. I think that there was an item in the chat on that. So I just want, you know, I think Susan's group and Xiaohong's group should be, you know, that would be of interest to them as well.
Yeah, thanks, Julio.
So Dan, did you have something else?
Oh, I was just saying that if for those that might have missed the ANWG meeting yesterday, that there's a document on the model development priorities, and I think it's open to comment, and Julio's set it up so that people can write on the second page ideas or things that they think are important. And so there is a geospace and chemistry section here, but if there are other critical things that this would be a good place to put things in. Right, Julio?
Did I hear my name?
Are you okay with Dan? Was Dan correct in saying this is a good place for us to include our chemistry requests?
Oh yeah,
document.
The document, sure. Yes. Sorry, I was checking an email.
No, that's quite all right. Yeah, I'll take notes if anyone has any thoughts they'd like to bring up here.
There's a question about MAD.
That must be for you to answer, Dan.
Yeah. We've done lots of evaluation on the chemistry side of it, comparing it to satellites and trying to understand how it improves the representation of the response to energetic particle events for NOx production at the high latitudes and its impact on ozone. So yeah, I think, and there have been some extended simulations trying to understand whether or not those effects in the upper stratosphere from energetic particles might propagate down to the surface. If you want to know some specific papers, I'm happy to share them. They're typically coming out of the group in FMI.
Cool. Thank you very much, Daniel. I will maybe drop an email to ask again.
Okay. Yeah.
Tack.
So anything else? What are people missing when they're running the model? Or are there other model developments that people are working on?
The model's perfect. We can all go home.
Okay, good.
Well, I must say that it hasn't been brought up in this meeting, but there does seem to be an issue with a difference between reanalysis and Wacom at the stratopause that we're trying to track down. We don't quite know yet whether or not it's got to do with differences in radiative transfer between what MERA uses and what we have. But there does seem to be 10 to 15K difference when we that we've noticed when we're doing our initialized forecasts, where we initialize it to MERA and then let it free run, and you see a big jump. So we're trying to track that down and wondering, and in fact, it looks like from preliminary comparisons to observations that maybe MERA is actually closer to OBS in the lower mesosphere. That's TBD really, but it's an ongoing project that, I think needs to get solved if we really want to do S2S prediction for the middle atmosphere and above.
And did you, I presume that you got sorted out that issue that originally was there with the diurnal averaging of the ozone that was fed to the radiative transfer?
No, this is all fully interactive chemistry we're doing these forecasts with. So that was only with Wacom with prescribed chemistry, prescribed ozone, that there was a bit of a heating bias there. But no, this is all just, the ozone does have its full cycle up there. So it's not related to that. I have a feeling though it could be related to RTMG being a bit tuned for the lower atmosphere and not really caring too much about the stratopause. So I'm hoping to get a different radiative transfer code in for a number of different ideas, like for instance being able to run with more extreme atmospheres by switching out to the Socrates radiative transfer code that the Met Office uses and seeing if that is better or at least gives different results, understanding some of the structural uncertainty that comes from the RT code. Nick, I don't know if you wanted to weigh in on the S2S for the upper atmosphere is kind of, a big interest of yours. I think it's a real opportunity.
Yeah, I would certainly agree. It's an opportunity. I don't have anything just like ready to show in terms of what you're saying, but it does certainly have an impact. If the temperatures change 10K within 2 days or something, that's certainly an issue in terms of analysis of any sort of forecasting in the evaluation there.
So I think there's actually another effort that got put on hold. And Rolando and I were trying to develop a 2-degree interactive QBO version of Wacom. And to do that, we had to go to 110 levels, similar to what Yaga has done with the 1 degree. And we got a really nice looking QBO, except then we ran into an issue with dehydration of the stratosphere, which is somehow coupled back to the convection routine. And so I think that's something that would be really nice to get handled. And I know CGD is working on that, but I just thought I would point that out, that that's something that could be very valuable for this community, because you don't always need to have a 1 degree model to look at middle atmosphere studies. And you don't even necessarily have to have TSMLT type chemistry. So I think it would be nice to have a faster model where universities could do some science with. So anyway.
Sort of related, I know there's interest in having a faster model for tropospheric chemistry, and some groups are still using the trope-Mozart mechanism, which is the old Mozart for chemistry. And I know I've said several times, but I will try to get a new trope-Mozart scheme running, that if you're looking at surface air quality and you don't need full stratospheric chemistry, particularly with specified dynamics and that sort of thing. I think there's still some interest in that. All right, well, if people don't have other things to say in the large group, there's a discussion in the chat. Stephanie, do you want to bring up in your questions?
Sorry, my internet connection is really bad right now. So,
okay.
But the question was, I can try to hang along if I just freeze or so. So the question was actually, since I originally came from astroparticle physics, I would really love to see a cosmic ray cascade code actually working at ESM, because then you would really see all the small scale effects in the atmosphere, like gravity waves and so on, if this would have an influence in the actual propagation of these particles from that perspective. And from the other perspective, it would be awesome to have the ionization channels of these particle cascades for example, lightning generation in the ESM.
Yeah, that sounds very interesting.
There's a group at CU working with Jeff Thayer that did at least the global electric circuit, and then was trying to tie that to lightning and those sort of effects as well, I think. And there was a presentation maybe 3 or 4 years ago in which they showed their parameterization, but I don't think it ever got into the release code. But I know there are other groups that work on ion-mediated nucleation for clouds, but no one's tied that to any enhancement you might get from ionization that occurs from galactic cosmic rays. So the pieces are around, I think, to do some of these things. They've just not been linked together.
Thanks, Daniel.
So people don't have anything else to say to the big group. we can try interacting in breakout rooms. We thought there might be, sort of nominal topics, but very informal and just a chance to chat with people. And the Elizabeth, are you there? It says
I am. I can go ahead and open the rooms.
Okay.
If you want to suggest topics, I can name the rooms with certain topics, or right now they're just numbered 1 through 7, and you can go ahead and.
So we had thought there might be 4 topics. People can here, put them in the chat. Just so people